Welcome to a new lecture. Today we'll be learning about Swin Transformer architecture. Swin Transformer is a natural extension to the two transformer architectures that we learned in the last few lectures, especially Vision Transformer and Data Efficient Image Transformer. So I originally thought we will first try to understand an intuition and then coding from scratch today, but Swin Transformer architecture is actually a little bit more complex. So I'm splitting this into two parts. In today's lecture, we'll be understanding an intuition, which I will also remind you to kind of brush up once before the next lecture. And next lecture, we will code a Swin Transformer from scratch. And code will be a little bit more complex than anything that we have done so far in this course. So I really want you to be on your full attention today and next week, because there are a few things about the implementation of Swin Transformer that are not so straightforward. I will also be putting out a video on a review of the Swin Transformer paper. So I have been going through the Swin Transformer paper in detail. The paper is really dense. It's from Microsoft. The paper has around 38,000 citations. I think it came out in 2021. And it's from Microsoft Asia research team. And they showed, probably in the most convincing way for the first time, that transformer architecture can become a good backbone for pretty much any kind of universal image task like classification, detection, segmentation, etc. So that's the relevance of this paper. But one thing I personally found from the paper is not written in the best possible way. It's very dense, and I wish they were not so frugal in terms of number of words while writing. But in any case, that's the reason why we will spend a lot of time on the architecture itself. So with that, the Swin Transformer architecture is basically a short form of shifted window transformer. So shifted, we'll see what is window and what is being shifted. It has a lot of things similar to Vision Transformer. So your past knowledge from how Vision Transformer works will be useful here, but there are also quite a lot of differences. And architecture, when I show you the architecture diagram, you will understand. So in Vision Transformer, it was doing this. In a brief nutshell, you had an image of height, width, and number of channels. And then this image was split into patches. Patches are basically non-overlapping, and each patch is considered as a token. And then we flatten these patches into like an array. So in this case, you have 9 patches representing the image, and then one patch is added as a classification token. And all these, one token is added as classification, and all these tokens also are added with position embedding. And then that whole sequence of tokens is what goes into the transformer architecture. And transformer architecture is something with self-attention without masking, because here the task is not next word prediction, because of which masked multi-head attention is not needed. It's unmasked. And then after going through attention, the CLS tokens context vector alone goes into MLP classification head. And then here you decide what class this particular image belongs to. In data efficient image transformer, we had some differences. One was an extra distillation token. Distillation token was appended at the very end, and distillation token was trained on the predictions made by the teacher model. Classification token was trained on the ground truth. In the last lecture, we saw how data efficient transformer can be much more lightweight. It was trained on just ImageNet 1K dataset. Now, a Vision Transformer, although this was great, it had a bunch of issues, specifically with respect to computation. So just look at this. If you have an image of, let me not show you this first. I'll just ask you, let's say you have an image of size I, or image of height H and width W. And let's say patch size is P. Totally, how many patches do you have in this whole image mathematically based on these 3 parameters? If you can mention in the chat the total number of patches. It should be, you have H by P patches along the height and W by P patches along the width. Total number of patch will be H by P multiplied by W by P, right? These many patches are there. And which means number of tokens is same as this. Number of tokens is same as number of patches because each patch is converted into one token. Now, if we were to construct self-attention, in self-attention, you have to do the dot product between query and key. So q dot key transpose and bunch of other things also. But when you perform this calculation, the order of magnitude of complexity is proportional to what? So if I were to say order of complexity of attention is proportional to what? Is it proportional to the number of tokens or is it proportional to something else? It must be proportional to the square of number of tokens. Why is that? Because you will have n queries and you will have n keys. And every single query is taken as a dot product with every single key. So the order of magnitude of this attention's complexity, attention computation complexity will scale with the square of number of tokens. Now, what is square of number of tokens? What is HW actually? What is the product of H and W? HW equal to what? In terms of image, what is this? It's a total number of pixels. You have H pixels along the height, W pixels along the width. So HW is basically image size if we were to denote image size by the total number of pixels. So from that point of view, in Vision Transformer, okay, Vision Transformer is great because you can construct global attention or long-range dependency between tokens that are geometrically far away. You can have a strong attention score between top left token and bottom right token. It's possible. But the complexity of attention calculation will scale with n square. N square is proportional to HW square, which is basically image size or number of pixels in the image. So basically, if you double your image size or if you double your resolution, your order of magnitude of the attention score calculation will go up by 4. The complexity will go up by a factor of 4. This is why it's called quadratic complex. So this was one issue with self-attention. It becomes immediately challenging for high resolution images. And if you want to perform tasks which are like semantic segmentation or instance segmentation, where every single pixel is classified instead of classifying the whole image or instead of drawing a bounding rectangle around the object, for such tasks, you need high resolution images. And high resolution images are always problematic for vision transformers. So here in this image, I'm showing you an example. So you have, let's say, number of tokens n equal to 5. Then you have 5 queries and 5 keys, which means your attention score or attention weight matrix will be 5 by 5. So basically it is scaling as n square. So if you have an image of height 80 and width 80 and patch size 16 by 16, you totally have 5 patches along the height and 5 patches along the width, which are 25 patches. If you increase the image size from 80 to 160, I mean, total number of pixels are becoming 4x, your attention complexity actually becomes 16x because you have 10 tokens along the height row and 10 tokens along the height. So totally now you have 100 tokens as queries and 100 tokens as keys. So 100 queries are attending to 100 keys. So 100 by 100, 10,000. So 625 order of complexity will become 10,000. So 4x increase in number of pixels result in 16x increase in complexity. So 16 is the square of 4. This is the problem with Vision Transformer. So what Swin Transformer does is it basically limits its attention to some local windows. So what I mean by local window is attention is not constructed by considering all these patches at once. It will construct a local window which may look like this. Something like, let's say this is a window of 2 by 2 tokens or 2 by 2 patches. So inside this window, only attention is calculated. Then inside this window, attention is calculated. Inside this window, it's calculated like this. So we will see why this leads to a better computational efficiency. Because in the paper, they claim that they have linear computational efficiency. We'll see why it is linear and not quadratic. And we'll also see some issues by converting attention from global thing into a local thing. So this Swin Transformer paper, it had 38,000 citations, and one of the biggest claims that they are making is, we know that Transformer has now become the backbone of NLP tasks, and CNN is considered to be the backbone of computer vision tasks. Transformer is still not like a general purpose backbone, but they are saying that from based on what they show, you can imagine Transformer to becoming a general purpose backbone for computer vision. What do we mean by general purpose? Any tasks, whether it's classification, image, object detection, or segmentation. For any of those tasks, it is possible to consider Transformer. And they accomplished something really, really amazing. So for all the three tasks, for image classification, they achieved 87.3% top one accuracy. This was actually close to state of the art or the state of the art at that time. Then on object detection, they achieved 58.7 average precision. For box average precision, and for mask average precision 51.1. We don't have to go into the details of how exactly average precision is calculated. I can share some lecture videos of my own where I have explained in detail what is average precision, what is mean average precision, etc. on another data set. And for semantic segmentation, they achieved mean IOU. IOU means intersection over union, which was better than the state of the art. So in short, they achieved or surpassed state of the art. Then they showed that attention complexity can be reduced from being quadratic to being linear. And they also showed that for broad level of tasks, because you can use this model, it can be considered as a general purpose model. One more important thing is the hierarchical nature of the vision. So hierarchical nature meaning, we'll come to this when we discuss the architecture, but vision transformer considered in all the transformer blocks 16 by 16 patches. So if the image had a resolution of 160 by 160, there were 10 patches along the row and 10 patches along the column. Here, on the other hand, patch size was different in different blocks of the transformer. So because of this, it could construct something called hierarchical feature construction. This is universally seen. I don't know how many of you know about UNet architecture. So if you search, if you look at this UNet architecture, which I had discussed in detail in one of the lectures, not part of this series, but separate. But here you can see that they are considering features of high spatial resolution and less channel dimensions. Then in the next layer, they are considering lower spatial resolution and more number of channels. Then lowest spatial resolution and even more number of channels, and then even lesser. So basically, they constructed UNet in such a way that features at different scales or different resolutions were used for making the final masking. UNet was primarily used for image segmentation. It is still being used in models like the equivalent of UNet architecture is still being used in models like stable diffusion. We'll see that towards the end of this series. But coming back to the paper, what they did, this was the architecture. Now, architecture is quite complex. You can see that, okay, first of all, let me draw a line to distinguish two things in the architecture. Everything to the right of this is figure B, okay? So this is not a continuation. What is shown here, over here, is this Swin transformer block, Swin transformer block, block. So there are 4 stages. In each stage, there is something, either a linear embedding or a patch merging. We'll discuss what those things are. Then in each stage, there is one Swin transformer block. One Swin transformer block consists of 2 things. One is a transformer block consisting of regular window. So this WMSA is regular window-based multi-head self-attention. Second is something called shifted window-based multi-head self-attention. So among this whole thing, the most difficult thing to understand, in my opinion, is this small thing. This is the most difficult thing, and this is where you should pay your most attention to. Now we have to understand a few things. First is, how do we construct windows? Second is, how do we do, let's say, position embedding? Then there is a question like, how does window-based multi-head self-attention work? Fourth is, how does shifted window work? Fifth is, let's say if this was a classification task, do we use a CLS token or is it something else? And how exactly is hierarchical features coming into picture? So if you can understand or if you can answer these questions, you basically understand the Swin transformer architecture. So we will go through it sequentially. Figure A and B. Yeah, of course, it's confusing. I'm yet to go through the figure, right? So figure A is the architecture. Figure B is the expansion of the Swin transformer block. This thing is expanded over here. And that consists of two things. But we'll come to that. I have not explained the architecture yet. But we have to understand how do we construct windows from patches? Because in Vision transformer, we had patches. Here you had patches and windows. How do we do position embedding? How do we construct these transformer blocks? Because if you look at the transformer block, if you zoom in, it's mostly similar with any other transformer block we have seen. You have layer normalization, followed by multi-head self-attention, followed by residual addition, followed by another layer normalization, followed by multi-layer perceptron. This we know, but only difference is now this is window multi-head self-attention and this is shifted window multi-head self-attention. Whatever output comes out of here, of the block number 1. So this we can call as block number 1 and this is block number 2. This output goes into the block number 2 as input. So we know these individual elements. We know what is MLP, what is linear layer normalization, what is multi-head self-attention, but we don't know what is window-based multi-head self-attention. How is it implemented in practice? We definitely don't know how does shifted window multi-head self-attention work, and we really don't know how it is implemented in practice. Now, I want to bring your attention to a few things. Let's start from the initial part. What is this image? Image is an RGB image with a certain height, certain width, and 3 channels, RGB channels. First thing that is done is this image is converted into patches, just like Vision transformer. So an image of H, W, and number of channels equal to 3 is divided into spatial patches of dimension 4 by 4. So every patch, so in Vision transformer, what was the patch size, if you remember? Do you remember the patch size of Vision transformer paper used in the Vision transformer paper? It was 16 by 16, right? The paper title itself was an image is worth 16 by 16 words. So it was 16 by 16 patches. Here, the patch size is 4 by 4, which means how many patches are there in my image total? In my image, in this case, how many patches are there totally? The total number of patches will be, I have H by 4 patches along the height multiplied by W by 4 patches along the width, because each patch is 4 by 4. So total number of patch will be H by 4 multiplied by W by 4. Now, if I were to represent every single patch by a vector which is constructed by concatenation of the values in my input image. My input image is this, okay? I have H as the height, W as the width, 3 is the number of channels. If I wanted to convert a patch into a vector where I'm just doing flattening operation, no other operations doing, what would be the dimension of my vector? How many numbers will my vector contain? I'm not talking about, yes, number of dimensions. Yes. Basically, my question is, let's say I'm considering every single number which is there in the input image. Okay. I'm not removing any number. I'm not adding performing any other operation. The only operation I'm doing is patching and flattening. At the end of it, I want every single patch represented as a vector of certain number of dimensions. Like that, you guys said I have H by 4 multiplied by W for these many patches. Now my question is, okay, I have these many patches and each patch is like a vector of certain number of dimensions. How many dimensions will my vector have? No, I just want a number. I want a mathematical number because you have all the information available for you here. I just want a number. What is the number of dimensions? that my patches have. So whoever said 48, why is it 48? So think about this. What is one patch? One patch is 4 by 4. But then I have 3 channels, RGB. Okay. So every patch has this much information. It has spatially 4 by 4 pixel worth of information. And channel wise, it has 3 channel worth of information. So the total number of pixel wise information for every patch is basically 4 times 4 times 3, which is 16 times 3, which is 48. So if I were to not take pooling or any operation like that, if I was simply flattening it into a vector, then I will have 48 dimensional vector corresponding to every patch. So now I have h by 4 patches multiplied by w by 4. So total number of patches is this multiplied by 48. This will be the total, representation of my whole image after patching and converting it into a concatenated vector. So that is the first thing that you should notice here. H by 4 multiplied by W4 multiplied by 48. So this 48 is the dimensionality of every patch. This is the number of patches along the height. This is the number of patches along the width. So these two, product of these two is the total number of patches. This is the total number of features in every single patch. Now what is done is, so that is what is done in the patch partition. So this, now patch partition does this. And now you also understand this. Now let's look at what does linear embedding do. What linear embedding does is, now you have a 48 dimensional vector. Linear embedding converts it into a C dimensional vector. C, I think they are using the character C to just denote channel dimension or something. But I don't think C was a good choice of dimension, good choice of variable. They could have picked something else. But anyways, whatever it is, 48 is converted into C. How do you convert 48 dimensional vector into a C dimensional vector? You use a matrix, right? You use a weight matrix, which basically looks like a linear projection. How does linear projection look like? In the layer number 1, you have 48 nodes. Layer number 2, you have C nodes. C can be whatever, and you have fully connected network here. And the value of these connections are basically the weights. The dimension of the matrix will be 48 by C, which means the input dimension is 1 by 48. Output dimension is 1 by C. So that is what this linear embedding does. So linear embedding converts 48 dimensional embedding into a C dimensional embedding. So by the time things come out here, this guy, what is going into the Swin transformer block will be H by 4 multiplied by W by 4 multiplied by C. This is the total number of patches. This is the dimensionality of each patch. Now, within the Swin transformer block, usually we know that dimensionality of the token is retained. Tokens do not change their dimensionality as it passes through the transformer block. Exact same thing happens here also. We are yet to look at the detail of the Swin transformer block. And here the reason why they have put multiplied by 2 is because Swin transformer block, there are 2 blocks. One is the regular window block and second one is the shifted window block. So please note this X2. It means just the block is repeating 2 times. Here the block is repeating 6 times. 6 times meaning regular, then shifted, then regular, shifted, like that. I have no idea how they came up with this 6. I can imagine why they came up with 2. 2 makes sense. 6 is probably empirical. Anyways, so what comes out of the Swin transformer block is also of the exact same dimension. Swin transformer block does not change the dimensionality. It simply converts every tokens into context vectors. So yeah, how many context vectors do you have here at the output of the Swin transformer block? Total number of context vectors. H by 4 multiplied by W by 4. Basically, that many context vectors are there. Each context vector is of dimension C. Now, here, something is done called patch merging. So before we go through patch merging, let's just discuss what is going into the input. So the output that comes out of the stage 2 Swin transformer block is H by 8 multiplied by W by 8 multiplied by 2C, which means what should go in here? What should be the input? Input should be the same, right? Because Swin transformer does not change the dimensionality of the token. So input should be the same as H by 8 multiplied by W8 multiplied by 2C. So from that, we can imagine what patch merging is doing is something where these tokens are converted into this somehow. We'll discuss how. But first tell me, are the number of tokens increasing or decreasing after patch merging? Number of tokens are obviously decreasing because total number of tokens here was HW by 16. Here it is HW by 64. So total number of tokens became 1/4, right? But the dimensionality of every single token became 2x. From C, it became 2x. This is kind of analogous little bit to what CNN does, because you know that in CNN also, as you go from layer 1, layer 2, layer 3, the spatial dimension reduces and channel dimension generally increases. You might remember that from vision language nano VLM lecture also. In general, spatial dimension reduces as you go from layer 1 to layer 2 to layer 3. Channel dimension increases, and you can see that that is what is happening. So spatial dimension, height is reduced by half, width is reduced by half, channel is increased by doubled. I mean, increasing by 2. In the stage 3 also that is happening. Stage 4 also that is what is happening. So here it is H by 16, W by 16, 4C. Here then 4C becomes 8C, H by 16 becomes H by 32. Now, what we have to understand is what exactly does patch merging do to make this happen. So what patch merging does is, if you have, let's say, 4 neighboring patches, I call this as patch number 0, 1, 2, 3. And let's say the dimensionality is C. Channel dimensionality is C. What patch merging does is a simple concatenation where all of these things are converted into a single token. Okay. Let me not put any number here, a single token. But if I'm just doing concatenation, what should be the dimensionality of this token? Channel dimensionality of this token? It should be 4C. So what happens is, here I had 2 by 2 patches. So this is not a pixel, it's a patch, please remember. So this 2 by 2 patch with C dimension, if I concatenate it into just a single patch dimension, my channel dimension will become 4C. Now think about my total image. My total image won't be just having 2 by 2 patches. My total image may have how many patches? Initially, it had H by what? H by 4 patches. Here I had W by 4 patches. And then this was C. Okay. Now, what will this become? Every 2 by 2 grid of patches will become just one patch. So H by 4 will become what? What happens to H by 4? See, along the height, 2 patches are getting merged into one. Along the width, 2 patches are getting merged into one. So height will get reduced by half, width will get reduced by half, meaning number of patches along the height gets reduced by half, number of patches along the width get reduced by half, right? Because every 2 by 2 patches, area of patches are getting converted into one patch. So what will happen is, this will become W by 8, just like how 2 by 2 became just 1 by 1, W by 4 will become W by 8. Sorry, the H by 8. This will become W by 8. And this will be what? What will this be? Why do you say 2C? It should be 4C, right? Because every 4 patches are getting converted into one patch effectively. So this should be 4C. Because think about it. Here, let's just put some value for H. Let's say H is 16. If H is 16, this was 4 by 4. Okay. And 4 by 4, 2 by 2 became 1 by 1, which means 4 by 4 should become 2 by 2, correct? So this will be 2 by 2. And what is H by 8? H by 8 is 2 by 2. So in the process of this 2 by 2 becoming 1 by 1, your C became 4C. Why? Because you are simply concatenating these 4 items of each C dimension one after the other. So C plus C plus C plus C, 4C. So this will be 4C only. The channel dimension will be 4C. Now, you might still be wondering, but we did not discuss 4C. We were in the architecture, you did not see 4C. In the architecture, actually, you are seeing 2C. How do you get 2C? How do you go from H by 8, W by 8, 4C to H by 8, W by 8, 2C? How do you do this? How do you go from this to this? What is happening here? You have H by 8 multiplied by W by 8 number of patches. Every patch had a dimensionality of 4C. Essentially, you are reducing the dimensionality, right? You are reducing the dimensionality of a token. Number of tokens reduced by 1/4. Now every token, every token is now reducing in spatial dimension also from 4C to 2C. How do you do that? Simple, linear embedding. Same thing, exact same thing what we did here. Whatever converted 48 dimensions to C dimension, same thing you can do here to go from 4C dimension to 2C. So you will have a linear projection layer where the first layer number 1 is of 4C number of nodes, layer number 2 is 2C nodes, and you will have fully connected connections going. And then that weight matrix of 4C, 2C dimensions will convert the channel dimension from 4C to 2C. Here, don't imagine an image. Just imagine you have H by 8 multiplied by W8, that many number of tokens. Each token is of 4C dimension. If you want to convert those tokens into 2C dimension, simply what will you do? You will simply use a linear projection. Exact same thing is happening here. So this is how you go from the H by 4, W by 4, C to H by 8, W by 8, 2C. And this step with this intermediate, 4C concatenated layer is what is happening in the patch merging. And now look at what has happened. You originally had how many tokens? H by 4 multiplied by W by 4 tokens. But now you have only H by 8 multiplied by W by 8 tokens in your image. So the number of tokens are now decreasing, right? So this is where the hierarchy, and here H by 8 tokens, W by 8 tokens. Although in each token you have now more information because you have 2C dimensions. So you can potentially add more information, but you have only less tokens. So you are looking at your whole image from a little bit more, I would say, abstract perspective, because the less number of tokens you have to represent your image, you are making it more and more abstract. If you remember from convolutional neural network, if your spatial dimension decreases tremendously, the image will become more and more abstract. So similar thing is what is happening here. And same thing repeats. In this patch merging, first H by 8, W by 8, 2C. After concatenation, what will this become? Just after concatenation, what would be the dimension of this? You are concatenating every 2 by 2 patches, which means H by 8 will become H by 16. W by 8 will become W by 16. 2C will become initially 8C. But then you do a linear projection from 8C to 4C such that over here, after linear projection, it will be 4C dimensional. Each token will be only of 4C dimension. It will not be 8C. So that is the input that goes into the stage 3 Swin Transformer block. That is the output that comes out of the stage 3 Swin Transformer block. And in this paper, they had these 4 stages, but in their ablation studies, you can see many different variants, but this is the best variant that they found. So this partially explains some things. I think partially you understand why there is a hierarchical nature, perhaps because the spatial dimension in terms of number of tokens is reducing, channel dimension is increasing. So in some blocks, in some stages, you are looking at more finer features. In some blocks, in some stages, you are looking at more coarse features. And then you are combining all of those to make your final prediction. So this is where the hierarchy comes. But you must have question, okay, patching also, I hope you understand. Patching part is simple because patching part is You just divide image into patches. If we concatenate h by 8, should it go to h by 4? No, we are concatenating. We are not. We are splitting. See, what we are doing is this is 2 by 2 by c. Now, if I concatenate this along the channel dimension, each of them will be one patch, and every patch will now have a dimension of 4c because you have 4 patches here to concatenate along the channel dimension. Now, like that, if I look at every 2 by 2 patch sets, so this is a 2 by 2 patch set, another 2 by 2 patch set will be here, another 2 by 2 patch set will be here. This will become like a 1 by 1, basically one patch of 4c dimension. This will become one patch of 4c. This will become one patch of 4c. Essentially, width will get reduced by half. So h by 4 will become h by 8. Height will become half. Similarly, width will also become half. So basically, h by 4 and w by 4 will become 1 by 8. C will become 4c. We are taking 2 by 2 patch merging. Is this a standard? I don't know why it should be a standard or whether it's a standard. I don't know the answer to either of that. I'm sure they might have tried maybe merging of more number of patches. Maybe the reason why they went with 2 by 2 patches, if you really want to if you really want to reduce the dimension spatially after h by 4 by h by 4, let's say you had to go to h by 6 and w by 6, something like that. I don't think it will be possible because how many can you merge along the row? Minimum number of things you can merge along the row is 2, right? Minimum number of things which you can merge along the column is also 2. So if you do that kind of merging, the minimum patch merging is basically a set of 2 by 2 patches. So I think they are just doing that minimum. I'm not sure if they tried merging a set of 3 by 3 patches. I have to check their ablation study, or merging a 4 by 4 patch. But you agree that you can't merge less than this in a symmetric way, because if you want to do it in a symmetry, width and height symmetry way, minimum is 2 along the width and 2 along the height. Now let us look at so you understand patches. Windows I have not explained yet, but I'll come to that. Now, the two things you understand from this is you understand that image is divided into patches. Patches are converted to tokens. Tokens are number of tokens reduced from one stage to another, and dimensionality of the tokens increase from one stage to another, and that is what is essentially creating the hierarchical nature. So these two you understand, but this is now remaining. What are windows? How are they created? Where is the position embedding coming into the picture? What is window-based multi-layer self-attention? What is shifted window? Are we having CLS token? How is finally, let's say, classification done? We will not be discussing detection yet or segmentation yet. Let's just stick with classification. How are these things done? So let's now move on to those aspects. Example with number of tokens. Yeah, for sure. If you have a 224 by 224 by 3 image, and let's say your patch size is 16 by 16, then what is 224 by 16? 224. 14. So basically, your input image will be converted to 14 by 14 patches, each of dimension. So if your patch is actually, let's not pick 16 by 16 because that is done in Vision Transformer. In this paper, it's 4 by 4. So let me keep it consistent. So 4 by 4 means you will have total 112 by 256 by 56 by 48. This will be your initial patch dimension. And let's say my input embed dimension is, let's keep it as 16 initially. Then after the linear projection, this will become 56 by 16. Now this 56 by 16 will go through stage 1. And what comes out of stage 1 is also 56 by 16. Now I need to do patch merging. Initially, after patch merging, this 56 by 16 will become 28 by 64. But then this 64 is projected into 38 dimension. Then it will become 28 by 32. And then this goes through stage 2. So this is what is the input into stage 2. What comes out of stage 2 is also the same by 32. And then happens patch merging. So after patch merging, this will become 14 by essentially 2C. I'm skipping the 4C step. So this will become 64. And then this goes into stage 3 and so on. We are yet to discuss after all of this, how is the final representation used for classification, that we will come to. But essentially, this is what happens. This complexity part I showed you. Okay, now, I know, I don't think I showed you. Well, let's discuss the complexity. Why do they say Vision transformer is quadratic and Swin is linear? Vision transformer being quadratic, you understand. Now let's focus on Swin. In Swin transformer, they do not construct attention between every single patch. So here, look at this. You have 224 pixels along the width and 224 along the height. And each patch, let's say if it is 16 by 16 pixels, I know that 16 by 16 is used in Vision transformer, but let's just keep it that way. There are total 14 by 14 patches, right? 14 patches along the width and 14 patches along the height. If it was Vision transformer, you will have total number of tokens equal to 14 multiplied by 14 equal to 196 tokens. In Vision transformer, in this, according to this example, you will have 196 tokens, correct? Which means the complexity will be proportional to n square, which is 196 square, if this was a Vision transformer. In Swin transformer, however, you construct something called as windows. So this red color thing is a window. In that window, in this one window, you have 7 by 7 patches. So now, if attention is constrained within this window, inside those window, how many tokens do I have? What is n inside this window? N equal to 7 times 7, right? There are 7 patches along the width, 7 patches along the height, 49 tokens or patches are there in my window, which means my attention complexity will be proportional to 49 square. Now let's keep this all in terms of some variables so that I can show you the linear and quadratic complexity. Let's start with Vision transformer. Width, height. Then patch size is P. Number of tokens equal to width WH by P square. Complexity of attention is order of n square, which is WH the whole square by P raised to 4. This is the order of magnitude. And if I just want to say it in terms of image size, basically complexity is quadratic with respect to image size in terms of number of pixels, right? This is clear. Now let's look at Swin transformer. In Swin transformer, let's say width is W, H is height, and patch size, let's keep it, let's say P or 4. Let's say patch size P equal to 4. And window size is M by M. Okay. Totally. And M by M is like number of patches along the width and number of patches along the height in one window. So by that logic, for one window, to calculate the attention, the number of tokens n equal to m square, correct? Because every window is consisting of m times m, that many number of patches or that many number of tokens. So for one window, I have total m square number of tokens. Now, that means the order of magnitude of attention complexity is again order of n square because I have n queries and n keys. And what is this? This is m raised to 4. But this is for one window. Like that, how many windows do I have? How many total windows do I have? In my whole image, how many windows are there? First, let me calculate how many patches are there. The number of patches, H by P multiplied by W by P. These many patches are there. So this is, let me keep it separate. Along the height, I have H by P patches. Along the width, I have W by P patches. Now, we said that one window along the width has M patches, which means how many windows are there along the width? this number divided by m. These many windows are there along the width. How many windows are along the height? These many windows are there along the height. How many are there? How many total windows are there? Product of these two. So total number of windows in my image will be HW divided by P square M square. This is the number of windows. How do I call this? Num windows. This is complexity per window. So then what is the total complexity? Total complexity will be complexity per window multiplied by number of windows. So m raised to 4 multiplied by HW divided by m square P square. This will turn out to be m square HW by P square. This is the attention complexity for the whole image in case of window-based self-attention. Now, is this linear or quadratic? It is linear because HW is the total number of pixels. So if you compare this with Vision Transformer, for Vision Transformer, it was HW the whole square. So if you compare the complexity, as the number of pixels double, the complexity here will become 4 times. Here, as the number of pixels double, total number of pixels is product of H and W. As the number of pixels double, the complexity does not become 4 times. It only becomes 2 times. But it becomes 2 times with a linear factor in front of it. But essentially, the scaling is linear. It's not quadratic. That's the important thing, right? So this is what I wanted to show you in this figure. I'll just show you quickly, but I have explained it already anyway. So in Swin Transformer, what they took is every window is 7 by 7 patches, and one token is basically equal to 1 patch. So every window will have that, for that reason, 49 tokens. And if there are 49 tokens, then attention complexity per window is simply n square, which is 49 square. And you have to multiply that with total number of windows. How many total number of windows will you have? Total number of windows will be roughly total number of patches along the width divided by number of patches per window. So it will be W by 7 times P. So here I should ideally put P also, but I was ignoring P. So ideally the divided by P square will come. And along the height, H by 7P. So total number of windows will be WH by 49 P square. Multiply that with the complexity per window, which is 49 square. You will get 49 WH divided by P square. So that is what I have written here, 49 WH. I mean, P square, when we are talking about order of magnitudes, you don't have to say these things. You just say it scales with WH. It scales linearly with WH. So this is the one of the biggest advantages of Swin. Now let's see, we discussed how the linear, I don't think I mentioned it here. Okay, windows I mentioned, right? So now you understand how windows work and how linearity comes. And this, let me put as 0th item. So now out of these things, you understand how patching works, how windows are there for making things linear, how hierarchy is coming in the from stage 1 to stage 2 to stage 4. And now we need to focus a little bit on these things. Okay. So first, let's discuss a little bit about one more thing, just the idea of non-overlapping window. Window is different from patches. Patches were non-overlapping, of course, but pixels form patches, patches form windows, windows form the full image. Okay, just remember that. So maybe 4 by 4 pixels form patches. Then okay, if I write it as pixels, 4 by 4 pixels form patches, 7 by 7 patches form windows. And then depending on the image resolution, something by something, let me call it as W by PM multiplied by H by PM. Those many windows form the full image. In Vision Transformer, we stopped at this stage. We just had patches. We did not have windows. The patches themselves created the full image. Here, that's not the case. Okay. Because window-based attention, is it weaker at capturing global attention, global context? It is definitely weaker because full global attention, full patches are not considered. But it cleverly fixes it. I'll show you how it fixes the issue. That's the whole reason why there is a there is a shifted window. So that is where I'm coming next. So you see that, see, if attention is restricted only to a window, okay, let's say let me go back to this image. Let's say I have a patch here and another patch here, and I have another patch here. So A, B, and C. Is there an attention between these two? Or if yes, what is that value? Let's call it as alpha BC. If B is query and C is considered as key, what will be alpha BC? Right, but what should be the value? It will be 0 here. The reason is, in Swin transformer, attention scores are constructed only between patches belonging to the same window. B and C, although according to the image, they are geometrically very close to each other, and perhaps there should be good attention between them. In Swin transformer, it does not care about the geometric proximity. It only cares whether those patches belong to the same window or not. So B and C, although they are very close to each other as a query key pair, the attention score between them will be 0. Alpha BC will be 0. However, B and A, although they are far away patches, the attention between those two will not be 0. So alpha BA will not be 0. There will be a finite attention between these two. Then you might have a natural question. Isn't this a problem? Because how come attention between B and C being 0? This is not very helpful, right? Of course, this is helpful to reduce the number of computations, that you understand. Computations became linear. So for bigger and bigger resolution images, this is good. But then, of course, this patch may have some dependency on this patch. So some long range dependency has to come, right? B and C, B and this patch number D, there should be some way for them to interact. How does it do that? This is, in my opinion, one of the worst written parts in the paper. Their choice of words are very frugal. It's very poor. And I struggled the most to understand exactly how it works. Then the only thing which helped me is I opened Figma and I tried to create a diagram of myself. And when I created it, then everything fell into its place. So I'll show you that figure basically. I'll first show you the figure and then I'll come back to all of this. So don't get frightened by seeing this. Let's just keep it simple. Okay. 0, 1, 2, 3. They are the window ID or patch ID. What are those? 0, 1, 2, 3 are window ID or patch ID. Window ID. They are 4 windows. A, B, C, D are patch IDs. Now, we know that in Swin transformer, there are 2 transformer blocks repeating again and again alternately, regular window and shifted window. So in regular window, creation of window from your patches are very straightforward. If you have 14 patches, you will have first 7 along the width forming the first windows, 7 to 14 forming the second window. So it's very clean, like this. Now, A and B are close to each other. A and C are close to each other. A and B are 2 patches belonging to with the same window ID. Window ID of A and window ID of B are 2. Window ID of A and window ID of C are different. Window ID of C is 0, which means attention between them in regular window, in the block number 1, it's null. However, when it comes to shifted window, what happens is, imagine that your original window was here. Let me just fill some color. Imagine your original window was here. This window is shifted by m by 2, where m is the width of the window. So by half of the window's height and half of the window's width, it is shifted. And the shifting is done in an interesting way. So if this gets shifted by m by 2, m by 2, essentially all windows get shifted by that. So now the windows will be over here, over here, over here, 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 like that. So essentially, to cover the whole image, right? How many unique windows do you need? Earlier, to cover the whole image, you needed 4 unique windows. Now, how many unique windows do you need to cover the full image after shifting? Forget the numbers. Ignore the numbers. Just follow the logic that I'm just mentioning. If you shift the window by m by 2 or width of the window by 2 by that factor, just look at this picture that I'm showing in front of you. Based on that, how many windows do you need? How many unique windows do you need to cover the whole image? You need 9 windows, 3 by 3. But this window, there is a problem. Firstly, only one of these windows are looking like the previous window. So this window number, which I have ID'd as 3, that window looks fine because it has 4 patches inside it. But window in which I have put ID 1 for now, ignore the ID, but this top middle window, this guy, has only 2 patches inside it. This corner window has only 1 patch inside it. The rest of the things are empty. Maybe then what you could do is, a logical thing which you could do is, you could do padding. You could pad some empty, zeros or something here. And then while constructing attention, you can say that if it's a padded patch, if it's a patch created during padding, the attention score between that patch and this should be 0. Between that and this should be 0. Between that and this should be 0, because padding is anyway something that you add extra. But to mathematically implement this, you could technically add padding so that the span of those 9 windows and the total span of your image are same. And then you say this is your window number 1 or 0. This is your window number 1. This is your window number 2, 3, 4, 5, like that up to 8. You have total 9 windows. And then you say that the local attention is constricted only to window number 0, or only to window number 1, or only to window number 2, and so on. In this, for window number 4, there is no problem because it has 4 patches. But for rest of the windows, the number of patches are less. That is one problem. Plus total number of windows increased. When you go from 4 windows to 9 windows, it's like what? 2.25x, right? Your total computation cost increases by 2.25x. Plus, it's not a clean thing because number of patches per window is not 4 anymore. In the previous regular window, number of patches per window was 4. So every window had 4 patches. Here, this window has only 1 patch. This window has only 2 patches. This window has only 2 patches. This has only 2. Only one window has all the 4 patches. So this is also a problem. So what is actually done in shifting is called as cyclic shifting. Cyclic shifting meaning whatever comes out of here is assumed to be come back up here. So if you are losing, essentially from 4 patches inside this window, only 1 is retained. Remaining 3 are going out of the frame. Then you are assuming that those 3 which are going out of the frame is rolling back and coming back here with the same ID. So I'm not talking about pixel values. I'm just talking about window IDs. Okay. Pixels are remaining the same. Picture is not rotating or anything. Just the window ID I'm talking about. So this window will have an ID of 0. This window will also have an ID of 0. This will have an ID of 0. This will have an ID of 0. And now if you look at this window with ID 0 altogether, it will have total 4 patches. I'll repeat. So what is done is, if you consider what has happened to this window after shifting, originally it had 4 patches, but now it has only 1 patch. But it will be great if window number, the top left window has 4 patches. It will be great because then computation will remain very similar to regular window. Regular window computation was easy because every window had 4 patches. Then you could construct attention score between 4 patches as query, 4 patches as key. Here, after shifting, the problem that has happened is some windows have only 1 patch, some have only 2, some only 1 window has all the 4 patches. Now, how do you fix this? Is padding a good answer? No, padding is not a good answer, mainly because if you pad, then you are adding some unnecessary extra computation. Instead of computing with 2 by 2 windows, you will end up computing with 3 by 3 windows. So that is one thing. So here what is done is something called as cyclic shifting, where let's say I have a window here. Okay. And if I shift it by half of the height up here, and whatever comes up it's like a snake game. You might have played this snake eating apple game, right? There, if the snake disappear up here, it comes back up from the bottom, right? Similarly, if snake disappears from the left, the snake comes back from the right. And if snake disappears like this in the corner, it comes back from here also, right? I hope you understand what I mean by that. So just like that, these walls, just imagine that if I am shifting the window up here, or for example, if I had a window like this, if I am shifting it up here, whatever goes out will come back from the bottom. If window is shifted to the right, whatever goes out from the right will come back from the left. If something is shifted to the left and right and to the corner, so here I am shifting this window essentially ended up reaching here. So I had a left shift, I had a top shift, then I had a top left shift essentially. So which means something will come out from the right because there was a left shift. So the 0 is coming out. It is appearing here also. Because you are shifting a little bit to the top also, a 0 is coming here. So to repeat, let me repeat once more. How do you go from here to here? You have to do top shift. You also have to do left shift. When you do top shift, what happens is, let me just draw here. And if this ID was, let's say the ID of this green color thing was 0. Okay. When I do top shift, these two patches will be 0, 0, and two patches are going up, which means this will become 0 and this will also become 0. Logic is clear, right? Then I have to do a left shift. When I do a left shift, this guy who was at 0 position will come here. And this guy who was at 0 or with ID 0, that will move here, which means whatever is going out here as 0 will reappear here as 0. Similarly, this guy who was having ID 0 would have gone here, and this guy with ID 0 will shift to the left. And what is gone outside, this 0 will come back here from the right. So that way, at the end of the day, by the time you do the shifting, and if you track the patch IDs, the green patch ID, if the original patch ID of this green color thing was 0, finally, this patch will have a window ID of 0. This patch will have a window ID of 0. This will have a window ID of 0. And this will have window ID of 0. And same thing happens to the rest of the patches. So you can follow this logic to understand that finally what will happen is these 4 corner patches will have same ID. This 2 patches over here at the bottom and these 2 patches at the top, they will have the same window ID. These 2 patches on the left and these 2 patches on the right will have the same window ID. Now look at what's the magic that is happening. Originally, I had, if you were to consider this if you were to consider these 4 patches, they never interacted with each other. Why? Because their window IDs were completely separate. Now, if you consider the same 4 patches, right? Now look at the same 4 patches. The ID of all those patches are now the same. The window ID of those 4 patches are 3, which means the patches that were not able to interact with each other or not able to attend to each other before in the regular window, they are now able to attend to each other in the shifted window. In the regular window, these patches were geometrically close to each other, but they were prevented from attending to each other because their window IDs were different. In the shifted window, those 4 patches, they are geometrically close to each other and their window ID are also the same. Now look at the next set. In regular window, if you were to look at this patch, this, and this. It will be great to construct a long range dependency, right? It would have been great to construct a long range dependency, but because these happen to be in different patches, different windows, these 4 patches, there was no possibility of constructing a dependency between them because there was no attention score between them. But now look at shifted window. In shifted window, those 4 patches are far away from each other, but a long range dependency is constructed between those patches because now they have the same window ID. So this is how shifted window attention will help different sections from your image to interact with each other by the combination of regular window and shifted window. Not because in one single window interaction between every single patches are allowed. That is not allowed. But by combining regular window first and then with shifted window, this indirectly allows for far away patches also to communicate with each other. And that is the reason why Swin Transformer performed as good as it performed, while maintaining the linearity of the complexity scaling with respect to the image size. So now from this eye, with this idea, if you look at, you can think of it as rolling on a cylinder. There are many ways to visualize this rolling, but basically it is like whatever goes out on one end comes out on the other end, instead of having like an infinite canvas or anything, right? The whole canvas is your image. So that is the idea behind window based self attention. Now there are a few more details which I want to explain. So let me show you 2 equations first, and then I'll explain everything else. So focus on just the regular window. Regular window is this block number 1. It's not called as regular window block. The only reason why I'm writing regular window here is because the multi-head self-attention is regular window based. So this is not called as regular window block for just today's explanation purpose. I'm calling it as a block with regular window. In that, your windows are like this. There is no shifting. How do you calculate attention score or attention weights? Attention is softmax of query times key transpose divided by square root of D. So you are considering ith query and jth key. You are taking dot product between them, square root of D softmax. But there is one extra term here, which you have never encountered in this course, at least yet. This extra term is the term that provides position information. This is called as relative position bias term. It's not called as position embedding. In Swin Transformer, they don't by default, at least the one that is written in the paper, they don't do position embedding, but rather they add something called as position bias. I will explain what this position bias is. But think about the main difference between Vision Transformer and Swin Transformer now. In Vision Transformer, where is position information added? At what point is position information added? It's added before transformer block. It's added at the tokenization step. You have patches. Patches are converted to tokens. To those tokens, you add the position information, correct? But here, look at where the position information is added. It is added within the multi-head self-attention, just before calculation of the attention weights. Now, this position term is a learnable term, so it's a learnable parameter. Now, this is for the regular window. Now, in regular window, all of these ij pairs come from the, let's say it's either from pixel patch number 0 to patch number 7 or patch number 6 along the row, and patch number 0 to patch number 6 along the column. So this ij, all of these ij pairs will come from the same window of the regular window. But if we apply the same logic in shifted window, that there will be a mistake. Why? Because in shifted window, patch number 0 to 6 do not all belong to the same window, because after shifting the window, this window would have shifted like, let me just delete this. If this is my window, this window would have shifted like this, which means in my shifted window, I cannot simply follow, just randomly take dot product between Qi and Kj, or I cannot randomly do this calculation and expect to get good weights and bias values. attention weight values. But what is done instead in shifted window block, the formula is slightly different. There is one additional term called mask ij. Now, what does mask ij term do? Very, very simple. Mask ij value, the value of this term will be 0 if the patch I and patch j have the same what? Same dash. The value of mask ij will be 0 if they have the same window ID. Basically, here what are tokens? Tokens are patches. If two patches belong to the same window, we don't need to do any masking or anything. Let them create attention between them. So if I and j are the IDs of or indices of two patches whose window ID happen to be the same, then the value of mask ij token is 0. Otherwise, if the query I and key j, which are two different patches, if they have different window IDs, then your mask ij value is negative infinity. Can anyone tell me why negative infinity? I mean, in Python, we can implement this by saying minus inf, or basically a huge negative number. Why? Because when you take softmax of a large negative number among a series of numbers, that value will be close to 0. That way, alpha ij, which is the attention score between query I and key j, will be 0 or close to 0, very close to 0, if the mask token is negative infinity. And if attention score will be, mask is not multiplied, it's just a number that is added. Look at this, it's just added. Please don't, this mask term is slightly different from the masking that is done in, let's say, mask dropout or something. Here is just a term that is added. So mask is one way to implement the shifted window. So this is just an implementation detail. You have to know this because otherwise in the next lecture, when we actually implement this, you will not understand why is this random mask term coming. So mask term is a nice mathematical, clever way to make sure that, if you have a large negative number, the numerator will be erased to minus infinity. Denominator will be erased to minus infinity plus bunch of other numbers, which means the softmax value corresponding to token, the query I and key j will be 0 because query I and key j do not have the same window ID. So this is how in practice masking is applied to prevent patches from two different window IDs from interacting with each other. Okay, so that being said, what else do we need to discuss? Let me just go back to our list of things. So you understand patches, you understand windows, you understand that there is something called as relative position embedding, but it's not complete. So this is next what I'm going to discuss. It's not position embedding, it's position bias. Here we are not adding anything to the token embedding. We are adding a bias at the query key inside the multi-head self-attention. You understand window-based multi-head self-attention because it's exactly same as self-attention, except it's constrained to windows. Bias term is added, mask term is not added. Inside the shifted window multi-head self-attention, there is bias term as well as the mask term. Mask term is minus infinity if two tokens have different window ID. It is 0 if they have the same window ID. Now, two more things we have to discuss for our understanding to be almost complete. One is, okay, position bias. I mentioned that it's a learnable term, but there is one more detail. And then about classification token. So after the context vector comes out of here, it's an 8C dimensional context vector. What happens? That also we need to discuss. So first, let me go into the detail of position embedding or position bias. So we are first of all constructing attention within a window, and I said that the window is 7 by 7, 7 by 7 patches, which means how many query key how many query key pairs can I construct for my window? Number of query key pairs. I'm not talking about number of query or number of key. I'm talking about query key pairs. All of you are making mistake. Number of queries is of course 49, right? Because there are total 49 tokens. So there are 49 queries and 49 keys, which means when I take query and key dot product, I can take any of the 49 queries and I can take dot product with any 49 keys. So totally I have 49 times 49. These many unique query key dot products available. What is this? I think this is 2401 or something. Let me. Yeah, so this is 2401. So in my attention formula, alpha ij equal to softmax of query I dot key j transpose divided by square root of d plus bias term plus the mask term, depending on whether it's shifted window or regular window. Here, how many bias terms do I need? How many learnable bias terms do I need? Because bias term is added with every query key dot product, which means ideally, if I have 2401 query key dot products, I need that many bias terms. So this is how we will think naively. But in the paper, what they show is something even more amazing. What they say is that you don't need 2401 bias terms because the exact positions, absolute position is not an issue. You just need the relative position. So if you look at the window, okay, inside this window, let's say I have uh, some patches. So patch number 1, 2, 3, and 4. So let's say for simplicity, my window is 4 by 4 patches. And let's say my query is this guy, and key is this. What is the relative shift if I were to say delta x comma delta y between key and query in this case? It is something like 1 comma 0. There is one position shift. Now, how many such query key pairs have such a 1 comma 0 shift between this query and this key is also delta x comma delta y equal to 1 comma 0? That is true. Between this and this, it's true. Between this and this, it's true. So for all of these query key pairs, if you look at relative shift between the query token and key token, it is the same. So you can somehow pass some sort of relative shift as the position bias. Now let's see how many such unique relative shifts are available. What are the range of values of delta x possible? If my window size is 7 by 7, not 4 by 4, it's 7 by 7. How many unique delta x values are possible? What is the minimum value of delta x? Minimum possible value of delta x. No, minimum value of delta x is what, 1 or 0 or something else? Minimum possible value is -6. Why? Because let's say my query is the last item and key is the 0th item. So this is 0 and or vice versa, but this is 0th item and this is the 6th item. So if you consider it like this, if this is query and this is key, from query to go to key, the shift is -6, correct? You have to jump 6 positions to the left side. So delta x can go from -6 all the way till what? Till +6. Because now key can be this and query can be this. Similarly, delta y can also go from -6 to +6. So how many numbers are these? These are 13 numbers counting 0. Because query and key can be literally the same token. Like this can be the query, that itself can be the key. Like same token can be used to construct query and key, as we know. That's the whole reason why it's called self-attention. You are paying attention to yourself. You have 13 unique relative shifts in y also, which means how many unique delta x, delta y pairs are possible? you have 13 multiplied by 13, which is 169 unique delta x delta y pairs are possible. So what is done in Swin Transformer is it constructs a table of 169 such unique delta x delta y pairs, but those 169 values are learnable parameters. So what is done is, let's say this is delta x, this is delta y, and this is bij. Okay. Then what is done is, now delta x can be 0, delta y can be 0, delta x can be -1, delta y can be 0, this can be -2, this can be 0, and many such values are possible. This might be -2.413, this might be -0.82, this might be +9.17. Bunch of these biases. So these are now learnable parameters. So what is done is, if the model is looking at token number I and j for query and key respectively, based on the I and j value, you can calculate how much is the delta x and how much is the delta y. Now, let's say the delta x and delta y happen to be -1, 0. Then what is done is, it will look up this table to pick this learnable value as the bij bias. If delta x delta y happen to be like 7, or 7 is not there, but 5, -6, then there will be some value, some learnable value associated with this. Like this, there are 169 unique learnable bij values corresponding to 169 unique delta x delta y pairs. And delta x and delta y is determined based on the ij values, because if I equal to, let's pick a random example. Let's say I is the row, j is the column. So let's say I comma j is, let's say I is this guy, and j is this. Then what is delta x? Delta x is equal to, in this case, -2, and delta y is 0, equal to 0. And then you look at the table, this is -2, 0. Then you say bij value is +917, right? This is +0.917. This is how the bias values are calculated in the Swin Transformer. In the paper, actually, they show 4 different cases. I'll show you one table. Yeah, so in this table, they have tried many different things. So they tried without position embedding, with absolute position embedding, not relative. Then they tried combination of absolute plus relative later. Then they tried relative position embedding without, I don't know what is this, without appending maybe. I don't know what is this appending referring to. I forgot. Then last is relative position embedding, which we discussed just now. And they saw that and you might wonder, like, the difference in accuracy between no position embedding and the best is like 10% or something. It's not like that. It's like 1%. This is 80.1 in ImageNet and this is 81.3. It's like 1.2%. So, but in the domain of computer vision, this is a huge deal. In computer vision, even 0.5% improvement or even 0.2% improvement is a very, very big deal, because that's how the field evolves. But you should be surprised to see this, because you might think like, oh, this is such a major thing. If I don't have position embedding, I'll have maybe 50% accuracy. That's not the case. Accuracy is still there, but it's few percentage points lesser. So they have tried everything. They have tried the normal absolute position embedding also. It's just that they found this to be better, relative position embedding to be better. So this is why it says, you can't predict which one will be better. If nobody had tried this before, it's impossible to predict beforehand whether relative or absolute, which one would have been better. Someone would have said, based on past experience, that, oh no, absolute position embedding is always better. But then somebody tried this and they figured out that relative position embedding is better. And then you can only explain it after the fact. So that is one interesting thing about, all these models. So that is about what? Position embedding bias. So we now know all these things. We now know how patching is done. Windows 7x7. Relative position embedding bias is bij. It is injected during the calculation of attention score. Window-based multi-head self-attention is normally calculated. The only thing is mask term is not there for this, but it will have a bias term inside the attention score calculation formula. Shifted window will have bij term plus mask ij term, whose value is 0 or -infinity or a big negative number. CLS token, this is the last thing, but before that, hierarchy is coming because your number of tokens are reducing from stage 1 to stage 2 to stage 3 to stage 4. But the the channel size or dimensionality of each token is increasing. Linearity is coming because you are looking at attention scores within one window. So within one window means it doesn't matter if the image resolution increases, your attention calculation complexity goes linearly with the image dimension. Now the last part, what do you do with this in Swin Transformer? What comes out of this? How do you utilize it for, let's say, image classification? That they explain in the, I think, in the appendix section of the paper. So yeah, look at this section. This is the appendix 2.1 section, image classification on ImageNet 1K. So 1K class classification. The image classification is performed by applying a global average pooling GAP layer on the output feature map of the last stage, followed by a linear classifier. We find this strategy to be as accurate as using an additional class token in Vision Transformer and DAT. In DAT, in fact, class and distill token was also there. In evaluation, the top one accuracy using a single crop is reported. So basically what is done is global average pooling, which is like, it's not max pooling, but it's basically a pooling operation that reduces the spatial dimensionality. So whatever comes out of this, a global average pooling is applied, which hopefully reduces the spatial dimensionality to 1 by 1. And the number of channels, I'm not sure. I think it will remain as 8C itself, if I'm not wrong. This I have to double check. This I'll check by the time we actually implement. And then there will be a linear projection layer or like a multi-layer perceptron. I don't know if they have a hidden layer in the linear projection or not. They just say a linear classifier. So I guess there is no hidden layer here. It's just 8C dimensional space to what will it be projecting to in this linear layer. Whatever is the number of classes. So if you are working on MNIST 10 class, if you're working on ImageNet 1K number of nodes. So let's say we work on MNIST next in the next lecture, you will have 10, which is the number of class. So this will be basically a matrix of dimension 8C multiplied by 10. If C is 16, it will be 16 multiplied by 8, whatever that number is, by 10. That will be the dimensionality of the matrix. And for this is for classification. For detection and segmentation is completely different. But we have not yet looked at transformers for detection, which we will look at after the Swin transformer is done. The detection transformer is yet to come. But this is essentially how Swin transformer works. I do plan to give you a couple of qualitative assignments, nothing, no coding assignment this week. I had posted, by the way, on Tuesday, 3 assignments. I hope you have seen on the dashboard. But this week's assignment will not be related to coding the Swin transformer, but it will be related to your conceptual understanding of the Swin transformer architecture, because I will need your conceptual understanding next week to kind of not repeat the same things which we discussed today in the next week's implementation lecture. So we will see that. Next week, we most likely will not have a lecture. We will have a break. After that, we will start with detection transformer. So so far, we have not implemented a single transformer for image object detection. We have only done image classification, but we need to look at DETR, detection transformer, which is probably one of the most famous transformers for detection, although there are better ones. And before that, please go through this lecture video. I'll be posting this as soon as it is compiled, and I'll be posting lecture notes. So go through all of that, plus go through the assignment. Then you will be fully prepared for the next lecture. Next lecture, please expect some heavy coding. The code is, as you can imagine, because so many things need to be implemented outside of Vision Transformer, it will be much more complex. But I think since we know the intuition now, we at least can save some time on the intuition part next lecture. So see you in the next week. Looking forward to seeing your assignments, and I hope you understood some things. If you have doubts, post on Discord. If you want clarity on some particular sections, just pause and rewatch those videos. Thank you so much. I hope you enjoyed today's lecture. In the next lecture, I'll also give you an overview of where the course is headed, like what all we have covered so far and where we are at right now. But from this point, transformers for classification, we will not be doing anymore, most likely. This will be the last model which we are discussing for classification. Now we'll be moving into a bit more complex things like detection. So see you again in the next lecture, and take care. Bye. Awesome. So welcome to a new lecture. Today we'll be coding a Swin transformer from scratch. So in the last lecture, I had given you an intuition about what is the architecture of Swin Transformer and how is it different from Vision Transformer. So I hope you have gone through the lecture as a recap, which I had mentioned yesterday. So you will require some prerequisite knowledge about the Swin Transformer architecture itself. I'll try to give you a brief recap, but most of the time today will be spent on coding itself. So that's the reason why I decided to split Swin Transformer into an intuition part and coding part, because combining both into one single lecture would be very difficult. And another comment which I want to make is today's coding, unlike Nano, VLM, or Vision Transformer models, it'll be much more difficult, simply because the architecture of Swin Transformer, when we go through it, you will see that there are many modules that we have to build from scratch. So it will not be easy. So you should be on your full attention, and most likely it may so happen that you will not understand certain parts, and that would definitely require a second round of you going through it or revising through it. So just expect that, but I'll try to cover as many questions or doubts as possible in today's lecture itself. So first, let's do a quick recap of what exactly is Swin Transformer. So Swin Transformer was introduced as a generalized transformer-based architecture for images. So they showed that in the paper, they showed that you can use Swin Transformer for image classification, object detection, semantic segmentation, etc. Although we will not be doing object detection or segmentation in today's lecture, we'll be focusing on classification. And the architecture is as shown in this diagram. So here, what is not shown is what happens to the context vector after it comes out of the transformer block. Then it has to go through something like a global average pooling, and then only the classification head comes. So if it's a 10 class classification, whatever is the number of nodes in the first layer, it will be connected to 10 nodes in the next layer. So this will be like a fully connected network. So this part is not shown in this architecture, simply because this will depend on whether our problem statement is classification or object detection or segmentation. But let's go through the architecture once very quickly. So you have images of height, width, and 3 channels. It can be 3 or 1 channel. Today we'll be looking at a 1 channel image, MNIST. So it will be H by W by 1. Then we convert the image into patches. So you know what patches are. Patches are splitting the image into non-overlapping small segments. And then patches are converted into flattened layer, so that every patch will have spatially only one dimensional, 1 by 1 as the spatial dimension, but number of channels could be something like 48 or whatever. And then a linear embedding layer basically projects all your patches into a dimensionality, embedding dimensionality of C. So from 48, you will go to whatever your embedding dimensionality is. And then what happens is you have Swin Transformer stages repeating. So this is stage 1, stage 2, stage 3, and stage 4. Today, we will not be having 4 stages. The main reason is that, the resolution of the MNIST image itself, if I'm not wrong, it's 28 by 28 or something, which means it's pointless to, divide the spatial dimension further to H by 16, H by 32, etc. So we won't be needing all the stages. We'll code 2 stages and we'll see. Then inside these stages, you have the Swin Transformer block, and that consists of these 2 things primarily. So this is the regular window on the left-hand side, regular window Swin Transformer block. And on the right-hand side, we have the shifted window transformer block. And just to refresh your memory, I have one question. So what's the difference between regular window and shifted window while calculating attention? So if attention is alpha ij between query I and key j, usually it is like this: softmax of qi kj transpose divided by square root of d. This is how usually attention weights are calculated. And then to get the context vector, you multiply it by value. But let's talk about attention weights. Alpha ij, this is your usual self-attention. But what is there extra in this regular Swin block? Is it the same as this formula, or am I missing something? There will be a relative positional bias term, right? So it's a relative position bias, meaning you look at every single patch inside a window and see how far away they are from each other. So there should be a bias term. We call it as Bij. So that is okay for regular. And for shifted window, is this enough or am I missing something? For shifted window, we discussed about a mask term. So mask term is we do not allow patches belonging to two different windows to pay attention to each other. So how do we prevent this whole thing? We introduce a masking term. So we can call that as mask ij. So if you don't have bij and mask ij, you have your normal attention. If you have this term, dot product of query and key plus the relative position embedding, you have your regular window. That to regular windows, multi-head self-attention. I'm only talking about this part right now. Everything else remains the same, just like the transformer. You have layer normalization, multi-head self-attention, skip connections, layer normalization, multi-layer perceptron. So everything is the same. The only difference is how does this window, regular window multi-head self-attention and shifted window multi-head self-attention look? So this is the normal multi-head self-attention. These two terms form part of regular window-based multi-head self-attention. And if you have these three terms, then you have shifted multi-head self-attention, shifted window multi-head self-attention. All right, so that is another thing. Now, I just want to show you a few things about what happens to our image. So let's take MNIST as the example. We have input image of height 28, width 28, and number of channels 1. It's basically black and white. So the original shape of an individual image will be C, H, W. C is channels, H is height, W is the width. So 1, 28, 28. This will be a single image. Now let's say we have a batch. I'm not going through the code right now. This is very familiar, but let me show you this image of one batch. So let's say my batch size is just 2 for simplicity so that I can show these batches as actual visuals. So my batch size is 2, meaning every single batch will have 2 images. So let's say these are the 2 images. Then it will add one more dimension, the batch dimension. So individual images height 28, width 28, number of channels 1. But then I have 2 images per batch. So those are these 2 images. Now, what do we do when we pass a batch into our Swin Transformer? What is the first step that we do? What do we do with our images? First thing, we convert to patches, right? Because in Vision Transformer, in all types of in Vision Transformer, data efficient transformer, everywhere we have to first convert image into somehow into tokens. The way of tokenization is patching. So we have to first convert to patches. So patch embedding, if you remember from the convolutional neural network lecture, was done using a line of code like this. So nn.con2d, so it will be basically a 2-dimensional convolution operation with learnable parameters, where if it is like con2d of 1, 48, 2, 2, can you tell me why is this value 1? What does this 1 mean? It is the number of channels in your input image. What is your input image? Input image is MNIST. MNIST has 1 channel. So this is the number of channels in the input. This is the number of channels in the output, which is equal to the number of filters. So why is this set to be 48? If you look at the Swin Transformer architecture, after patching, you end up with a 48 channel set of images or 48 channel patches. So that's why we set it to be 48. Then this 2 is kernel size, and this is also stride, which is 2, which means now we will create non-overlapping patches. And what will be the patch size according to this? The size of each patch. It has to be 2 by 2, right? Because your kernel size is 2 and each kernel becomes 1 patch. So at the starting, each patch will be of 2 by 2 size. So now if my image has height h originally and width w, how many total patches will I have? I should have h by 2 patches along the height multiplied by w by 2 patches along the width. So total number of patches will be hw by 4. So what will happen is, so here after this con2d operation, the 2 images which I had, so this is image number 1 and this is image number 2. these are the two images that I have in my batch. Its spatial resolution will shrink by half. It will become 14 from 28. Why? Because each patch is 2 by 2. And number of channels will increase to 48 because number of channels in the output is equal to number of filters, which I define in my con2D. So now I have two images of spatial resolution 14 by 14 and channel resolution 48. All right. Now, after patch embedding, what do we do? In the Swin Transformer, I can actually show you the image. So after patch embedding, what is the thing that we do? We do linear embedding. And in linear embedding, what exactly are we doing to each patch? We project it from a 48 dimensional space into a C dimensional space. The value of C is variable, but so we can see what value we can use for C. But basically, it's a linear projection, right? So you create the token embeddings of C dimensions. And how many such tokens are there? You have H by, in this case, they are using H by 4, W by 4, but here I'm showing you a different example. Okay, so here I'm showing H by 2, W by 2. The only reason why I did that was, otherwise, if I use H by 4, W by 4, in this case, it will be a bit difficult. I may have to draw more items. So let's keep it this way. So don't get confused. Here, I just showed you an example where my dimensionality at the output is 14 by 14. But according to the paper, it is H by 4, W by 4. I'll also show you why we are doing this. Because when I divide my MNIST image too much, even after 2 times you divide by 2, 28 will become 14, 14 will become 7. And after that, it's not perfectly divisible by 2. So it's just an artifact of MNIST being a low resolution image. So that's the only reason why I'm not dividing by a bigger number at the starting itself. Okay. So that will be, so now output will look like this. 2, 48, 14, 14. Now tell me, what is this 2? It's the batch size. What is 48? 48 is the number of channels in my output image just before linear embedding. Then 14 by 14 is what? This is the height of each patch and width of each, height of each image and width of each image after con2D operation. And then we will project this from a 48 dimensional into a C dimensional vector. But for simplicity, we can assume that C is also equal to 48. So after projection, ideally this should become 2, C, 14, 14, something like this. But if C is equal to 48, we'll say this will remain as 2, 14, 48, 14, 14. This is just for simplicity. Okay, so that we are not using too many variables in our visualization. While coding, of course, we can mention C as a separate variable. Then, so this is the flattening operation. So flattening operation happens so that, so this happens actually just before linear embedding. I should have shown you this first. So flattening operation converts every patch. So what is my patch size? It was 14 by 14. My image size was 14 by 14 after con2D operation. And this had 48 dimensions. All right. And then like this, I had 2 images. And what will happen is I will have now each patch will be, I just want what each image should be a certain number of patches. And in the flatten operation, what I will do is all the 48 channels I'll pick. And then I have one image here, right? So this one pixel, not one image, this one pixel has 48 dimensions. Then what I will say is, not one pixel, a 2 by 2 pixel, it will have 48 dimensions. So if we were to think about a 28 by 28 image and a 2 by 2 pixel patch here, okay, this will have 48 dimensions. And ideally, my one token is equal to one patch. So what should I say? What I should say, I should somehow be able to extract all these patches as independent tokens so that now I have a sequence of tokens, because finally what goes into the transformer is a sequence of tokens. It's not an image. And how do we get sequence of tokens? By performing a flattening operation. So if I had 2 by 2 patch, and if my image size is 28 by 28, and if the channel dimension is 48, how many total number of tokens are there, or how many total number of patches are there per image? Per image, I will have 28 by 2 multiplied by 28 by 2. So 14 by 14, which is 196 tokens or patches per image. And the dimensionality of these tokens just before linear embedding will be 48. So every image, so this is image number 1 and this is image number 2. Image number 1 will now be split into 196 patches equal to 196 tokens. Okay, so each image will become a sequence of 196 tokens, and each token has a dimensionality of 48. So now if you look at this, this is basically now one patch. Something that looks like this with 196 dimensions. And so now we have these things. We have batch size. So this was the input that was going into the flatten operation. I have batch size of 2. I had 48 as the dimensionality. Actually, this will be converted into a one single number. But if you were to look at one single patch, if you were to just imagine that you have one single patch, I'm just talking, okay, without flattening. Just before flattening, if you were to look at what exactly are each of those components are spatially one patch of channel dimension 48. Flattening operation will make sure that it has only the channel dimensionality. Spatially, it will be 1 by 1. And then it will be treated like a vector of 48 dimensions, right? And then that 48 dimensional vector is what is projected into a C dimensional space. So when you go from the input of this linear embedding to output of the linear embedding, you are converting each vectors of spatial dimension 1 by 1 and channel dimension 48 into a vector of dimensionality C. All right. When we code, this will be much more clearer now. So what we want to do is, we had 2 by 48 by 14 by 14. We'll go from this to something like this. So what has happened is, this 14 by 14, if you multiply 14 and 14, you have 196. So totally, you have 196 tokens. How did we get 14 by 14 in the first place? 14 was the number of patches along the height. This 14 was the number of patches along the width. So you basically have a 2D grid of patches. Now those 2D grid of patches, you convert into just a one-dimensional set of sequence. So this 14 by 14 will be combined into become just a sequence of 196 patches or 196 tokens. This 48 will remain here. So this 48 is the dimensionality of each patch. And then first item is the batch size. So now just read this. What we are saying is, in my batch, I have 2 images. Each image is consisting of 196 tokens. Yes, it is flattened. So the code here is x.flatten of 2, meaning this dimension will be flattened. Everything after this. So this is dimension number 0. This is dimension number 1. This is dimension 2, 3. So everything after this will be flattened into one single thing. So you will have only 0, 1, and 2 dimension. And then you transpose dimension number 1, 2. Why did you take the transpose here? What is the purpose of this transpose 1, 2? What you want is, you want the dimensionality of your token as the last dimension. So if your token is 48 dimensional token, that should come at the very end. So that's the reason why you first flatten and then you take the transpose. So just to reiterate, the sequence of tokens that you have are, you have a batch size of 2. So you had 2 images. Each image you split into patches of 2 by 2 size. So totally, since you started with 28 by 28 images, you ended up having 196 patches or 196 tokens per image. And each token is of dimension 48. And now you can project this into from 48 to, let's say, C dimension. So C 2, 196, C from here. And here we can assume that C is equal to 48 or whatever we want to use, right? So this is what is happening. So now you have two batches, 196 tokens per image, and C is the dimensionality of each token. Now, these linear, this sequence of tokens is what is being passed into the Swin transformer block. Now, let's look at what happens inside the Swin transformer block. So inside Swin transformer, just imagine, what is the input to the Swin transformer block. There are two blocks, by the way. You have regular window block and you have shifted window. I don't want to call it as block. Maybe a better term is a regular window MSA based transformer block and shifted window multi-gate self-attention based transformer block. So first is you are getting the feature map. Feature map meaning you don't have the image in its original shape. It has passed through a few layers. So you have a bunch of features that is being passed into the Swin block. And before going into any of this, just think about what these 2, 3, 4, 5, 6 steps are. If we are in a regular window block, there is no shifting, right? In regular window, there is no window shifting. So window shifting, I hope you vaguely remember. So window shifting is nothing but, we said that in the regular window, the windows are consisting of patches. So here in this example image, each window is a 4x4 patch. So pixels make patches, patches make windows, and windows make the full image. So here, this is a patch, 4x4 patches make a window. So now this is a window. In this case, 2x2 window make the full image. And this is what is happening in regular window. In shifted window, what happens is you perform something called as window shifting. So if the window size was, let's say 4, your shifting will be done by a magnitude of 4x2. So now what you will have is you will have a window here, you will have a window here, a window here. So instead of now having 4 windows, you will have 9 windows. But you don't want the number of windows to increase. So I had shown you a figure in the last lecture. Yeah, so this figure. So you don't want the number of windows to increase. So what you will do is you will assign IDs to the windows. So in the original regular window, the ID was, this whole window was of ID 0. This whole thing was ID 1. This whole thing was ID 2. And this whole thing was ID 3. In shifted window, what we do is this window is ID 0. This window meaning basically this particular part of the window. This is ID 0. This is 0. This is 0. This is 0. Then this is 2, this is 2, this is 1, this is 1, and this is 3. So in shifted window block, we have patches that are far away from each other having the same window ID. Now, what is so special about window ID? Why did we do this? So when we pay attention, when one patch pays attention to another patch in the image, attention scores are only constructed if their window IDs are the same, meaning this window can pay attention to this window, although they are far away from each other. This patch. But this patch cannot pay attention to this patch, although they are close to each other because their window IDs are different. The window ID of the left-hand side patch is 0, window ID of the right-hand side patch is 1. But that is not a problem. Why is that not a problem? Because in the regular window, they were anyway paying attention to each other. So because those two patches belong to the same window. But in shifted window, now the shifting is allowing patches that were far away from each other to pay attention to each other. So this is how you are able to construct long-range dependency in shifted window setup of the Swin transformer. And we also discussed why this is so beneficial. It was because the complexity of attention calculation was dash. Complexity of attention calculation was growing in dash format with respect to the image size. No, it was linear, right? In Swin transformer, it was linear. In normal transformer, in Vision transformer, it was quadratic. So that was the main reason why we went with this shifted window idea. I mean, not we, the authors of the paper went with the shifted window idea, because the window size inside which tokens slash patches pay attention to each other, it remains the same. Window size does not change even if the image size changes. All right. Every attention is caught by both regular and shifted window. It's not like every attention is caught. In regular window, attention is paid by patches that are physically close to each other or geometrically close to each other. In shifted window, you don't necessarily have patches that are geometrically close to each other. So you have localized attention as well as kind of global attention. I don't want to say it's a perfectly global attention. If it was perfectly global, we will not restrict the patches to be inside windows, but the patches can technically be very far apart in the shifted window. So this is the shifting that we are doing. So now, if we are using a shifted window, we apply this window rolling. So window rolling is just the term that we use to describe the fact that you are shifting the window by W by 2 and W by 2 to the left and to the top. So if we are in a shifted window block, we will apply rolling, but this step will be skipped if we are in a regular window. Now, in a shifted window, if we are rolling, we have to, after applying attention and everything, we have to roll it back. Because if you go to the transformer architecture, see here there are multiplied by 2. Multiplied by 2 meaning you have one regular window and one shifted window. But in some stages, it's like multiplied by 6, meaning you have regular window, shifted window, regular window, shifted window, and one more repeat. Which means whatever comes out of the shifted window, right? You should not have that shifted window now again going back into a regular window. So the shifting you have to reverse once your attention computation is done. So we'll come to this attention computation part, this 2 and 3, 4, and 5. But basically, if we were in a shifted window where this shifting operation was applied, we have to roll it back so that window comes back to regular. Now we can pass this. So these operations will happen in regular window. And then same operations will happen in shifted window, except in shifted window, this window rolling and rolling back is not needed. It is not done. But if it's a shifted window, the rolling is done before attention calculation and rolling back is done after attention calculation. Now, this part is easiest, I would say. 7th, you will know. I mean, multi-residual adding and multi-layer perceptron. So this part I don't have to explain too much. But let's come to 3, 4, and 5. Now think about this. I have an image of certain dimension and or I have a set of patches of certain dimension, and but I am not paying attention inside the total image. So if I have a sequence of 196 patches or 196 tokens, I'm not going to use all these 196 windows, 196 tokens in each of my attention calculation, right? I want it based on window. So for attention calculation in the regular window block as well as in shifted window block, it is not very helpful to me if I get the whole sequence of tokens as one sequence. What I want is I want tokens based on windows. So something called window partition we will be doing, which partitions the whole set of tokens into different windows, so that we can only focus on one window at a time. Then within each window, we will calculate the attention. So within each window, I'll have multiple patches. Those patches will attend to each other. And then I will do something called window reverse, so that my dimensionality, if the dimensionality is like batch, tokens, token dimensionality, if that is the dimensionality that was there before we did the window partition, we will reverse that operation so that my original dimensionality is back. Okay, there are a couple of questions. Suppose the object is in right corner, another is in left. How to capture global? Yeah, so just check this. Where is my visual example? So if the object was in the, one was in the right corner and another was in the left. So this, you look at in the shifted window, this has window ID 2 and this has window ID 2. So in that case, it is automatically paying attention to each other. So it's like shifted window is like a complement of regular window in the sense that in shifted window, if you look at this patch, this patch, this patch, and this patch, although they are all 4 patches very close to each other, there was no attention between them because their window IDs were different. But that problem is solved in this case. Conversely, you had 4 corner patches which were not paying attention to each other at all. That problem is also fixed. So basically, the problem of objects being far away from each other or closer to each other, none of that is an issue. By shifting by half window, will we find attention to all patches in the shifted window? Is there a chance that we miss a few patches in attention? Yes, there is a chance that we miss a few patches in attention, of course. I can already think of an example. So let's say I take an example of this patch. Let me first delete all this annotations. Okay, let's say I am considering this patch, and maybe this one. Okay. And now look at the same 2 patches in shifted window. In regular window, am I drawing the same? Yeah, I think this is correct. So in regular window as well as in shifted window, those 2 patches are never able to pay attention to each other, because in regular window, the ID was 2 and 3. In shifted window also, their ID happened to be 2 and 3. So here, obviously, this patch will never be able to pay attention to this patch in regular window as well as in shifted window. But that's I would say, the downside of Swin that we have to live with, right? We will not get everything. So if we are getting the benefit of linear progression in complexity, there must be some downside. The downside is this: it's not a perfectly global attention. It's not like every single patch will pay attention to every single other patch in shifted window attention, but it solves the problem to some extent. And the hope is that when you go through, if you look at the feature dimensionality, I mean, not the feature, the spatial dimensionality, you go from h by 8, then h by 16, h by 32. There is already a lot of abstractions that we are capturing, and we are hoping that by keeping the same regular window and shifted window, we are hoping that somehow all the features will be captured in multiple stages. So maybe the reason why people thought of multi-stage Swin transformer is because in one stage it may not result in good accuracy, probably because of the exact same reason that some patches never get to see each other in the attention. All right, so that is the whole idea of the Swin block. Now, what else is remaining before we move ahead? This I showed you already. Yeah, so now this is the part where we convert sequence of tokens into windows. So let's say my window size is 7 by 7. So let's say my window size is 7 by 7. What does this mean? Does this mean that I have 7 pixels by 7 pixels in my window? Are these the number of pixels or something else? These are the number of patches per window. So if I say that my window size is 7 by 7, it means each window has 49 patches. Now, look at this image. So this is what we have after our embedding. So let's say my embedding dimension is also C is equal to 48. Okay, so don't get confused. So this here, I'm assuming that C is equal to 48. Each image number 1, I have 196 patches. Image number 2, I have 196 patches. Now, if I am splitting this into windows, tell me how many windows will be there in each image? (196) divided by 49, which is 4. 49 times 2 is 98. 98 times 2 is 196. So basically, each image will now be split into 4 windows, correct? And the channel dimension will not change. Channel dimension will remain the same. It will be 48. So after converting my patches into windows, now I have a window size of 7 by 7, which means I have 7 patches along the row and 7 patches along the column, consisting 49 patches. Like that, image number 1, this is the image number 1 in my batch, will have 4 windows. So this is window number 1, window number 2, number 3, and number 4. But the channel dimension will remain 48. Similarly, my image number 2 will also have 4 windows, channel dimension remaining the same. Now, Are we paying attention like this? Is attention constructed from here to here between this window and this window, and between this window and this window, and between this window and this window? Is that how it works? No, that is not how it works. Attention is restricted to just the windows. Attention is not there between windows. What that means is within this window, I said I have patches, right? So I have patches inside this window. Those patches will pay attention to each other. So my regular window, shifted window, etc. are being applied within these windows. So if my regular window was like this, my shifted window will look like this. I mean, I just drew it on another window, but basically I just want to show you. So attention is constructed within window number 1 separately, within window number 2 separately, number 3 separately, number 4 separately. There is no attention between the windows. So for that purpose, although I have, so what is the batch size here? Batch size is 2. So if we were to write the dimensionality, it is 2 comma, then how many windows I have? 4 windows I have. And that too I can write maybe something like, okay, let's keep it like this. Then each window is something like 48 dimensionality, right? So 4 windows and I have 49 tokens. Yeah, 7 by 7 tokens per window. And then each token has a dimensionality of 48. So let's say this is my batch dimension. This is my number of windows per image. This is the number of patches along the width, number of patches along the height, and this is the dimensionality of each patch. I don't have to now make this batch-wise separation anymore because anyway, it doesn't matter. Within the same batch itself, I am considering windows separately. Within the same batch itself, I have 4 windows. Those 4 windows are counted separately, which means I can count all these 8 windows by saying that totally I have 8 windows. Each window has patches of size 2 by 2, or rather dimensionality of 48. And what else? Yeah, I have 7 patches along the width and 7 patches along the height per window. So 7 by 7 is not the, it's already flattened. Please note, 7 by 7 is the patch number. It's not the patch dimension. It's not the pixels per patch. It is the total number of patches in the window. Total pixels in the patch was already flattened before, right? So what this says is, in my current batch, in my total batch, I had 2 images, but then when I split the image into windows, each image became 4 windows. And because I'm paying attention within the window, I don't care about batch separation anymore for purpose of calculating the attention. I can take all the 8 windows, out of which 4 windows are coming from first image and 4 windows are coming from second image, but I can group them together because I'm anyway considering windows separately for my attention purpose. And then here I'm saying I have 7 within each window. So I have totally 8 windows. Within each window, I have 7 patches along the width, 7 patches along the height, and each patch has a dimensionality of 48. So now this is what will go through my attention head, multi-head attention. And for each of these 8 windows, attention will be calculated separately. And once it comes out of the attention, we will reshape it back into this because the batch dimensionality has to be preserved outside of the multi-head attention when it goes to multi-layer perceptron and other modules. But for the purpose of calculating attention inside the attention head, we don't need to preserve the batch dimension. We'll see that the implementation of this in the coding. Window attention. Yeah, this we already discussed. I'll come back to this if needed. I think now we are ready to start coding. I don't think that I have missed anything important. If I have, I will explain it during the coding. So now please open Google Colab. Let's start from scratch. We'll take a 2-minute break and let's reconvene to start coding. And here, please, pay full attention because the code is a little bit long, but I hope we can get it working by the end of today. All right, let's continue. So the things that we have to code today, we need to code importing. Then we have to define certain functions. For one is window partition functions, one for window. I mean, all of you can see my Colab notebook, right now? Just to confirm. Okay, awesome. So we need to do window partition. Where do we do this? Just before we go to the attention stage. Then after attention, we have to put the windows back into image format. So then we have to code something like window reverse. Then I'll paste the link. And then we have to code some classes. So one class for window attention, which is basically calculating attention scores or self-attention within each window. Second is we need one for the swing block. This will include both the regular swing window and shifted window. Then third is we have something called patch merging. This is something which I did not discuss today, but we had discussed in the last class. So do you remember what we were doing in patch merging? In patch merging, what we did was, let me go back to the diagram, was something like this. So we wanted to go from a dimensionality of, let's say, h by 4, w by 4, and c to h by 8, w by 8, and 2c. So if you look at the Swin transformer figure, you see it goes from h by 4, w by 4, c to h by 8, w by 8, 2c. But we also had discussed in the last lecture that the dimensionality does not change as the patches go through the Swin transformer block, which means if the output that is coming out of the Swin transformer is h by 8, w by 8, 2c, the input that goes in also has to be h by 8, w by 8, 2c, which means this patch merging is doing something which is converting h by 4, w by 4, c to h by 8, w by 8, 2c. And there what we did was there was an intermediate stage which first divided the h by 4 and w by 4 into patches of size 2 by 2 or groups of patches of 2 by 2. And then it performed a flattening of those individual groups. So then what happened was, instead of now having h by 4 and w by 4, it got divided. The height became one more factor of 1 by 2, which means h by 4 became h by 8. Width was divided by a factor of or multiplied by a factor of 1 by 2, which means w by 4 became w by 8. But then these 4 items, right? There are 4 items inside each group of patches. They were concatenated to increase the channel dimensionality from C to 4C, because you have 4 items each of dimensionality, channel dimensionality C. So they were concatenated after each other to form 4C. And then after this, there was a linear projection. So the way you go from 4C to 2C, they had a linear embedding where each item was taken separately and each item had a channel dimension of 4C. And after a linear embedding, you get 2C. So this is what they did. And this is what we called as patch merging, not embedding. So we have to have something for patch merge. And then we can have a final, let's say, multi-stage Swin transformer class. So this is just for the Swin block, but this is for the whole transformer with MNIST data. We'll use MNIST. So these are the classes we have to define. Then we have to download the data set. Then we do the training and testing. So these are the things we are going to implement today. Okay. So let's start with imports. So first, always we import PyTorch. Then import torch.nn as nn. And this is for passing into the classes so that classes can inherit properties from nn.module. Then import torch.nn.functional as f, which will be used while performing layer normalization. Then from torch vision, import data sets for importing PyTorch, importing MNIST from PyTorch library. Then we need some data transformations like mean value normalization and standard deviation shifting from torch.utils.data, import data loader for converting the images into batches. Then this is optional from TQDM, import TQDM. I always knew what is TQDM. It is for displaying the progress bar, but I did not know the full form. Does anyone know the full form of TQDM? It's a weird word. TQDM, it's like some Arabic word. TQDM PyTorch full form. This is the Arabic word. I don't even know how to pronounce this, but basically it in Arabic it means progress. So this is how TQDM came. Anyways, so this is for just displaying the progress bar while downloading the data set or displaying the progress during epochs. So that's all the imports. I don't think we need any more. I have Collab Pro, so I will be connecting to TPU. You can feel free to connect to whatever resource available to you. It's reasonably fast even without Collab Pro. The training is not too slow. Now, after imports, we need to implement these two things, window partition and window reverse. So let me just, these two functions, let's define. So define window partition, and some input should go. One is, of course, the input batches itself, the image batches. Second is some window size, because to partition something into window, we need to know what is the window size. So this is the first function, and something we need to return at the end of it. Second function is window reverse. After partitioning, the partition thing goes to the attention, and after coming out from attention, we have to put it back into image format. So we can define window reverse. And here, the input here will not be X, because we won't have the original X anymore. Input will be whatever windows we have. The windows that went through the attention block and that is coming out of the attention will be one of the inputs here. Another input will be how many windows we have, that we will know, then width and height. So this information we'll have, and then at the end of this, we have to return something. So what we are returning in both cases, we can return just X, and we just need to perform some computation before returning. So first is, I need to know what is my batch size, what is my height, what is my width, what is the channel dimension, and all of this is simply available from x.shape. So this will give me what is my batch size, what is my height, width, and C channel dimension. Then what we do is x equal to x.view. So now think about what we want to do. The height we want to split into windows, width we want to split into windows, right? That's what we want to do. So I want to reshape this such that b comma height divided by windows, but here instead of using simple divided by, I'll use 2 bars, which means it will consider the integer. Then but then the total dimension has to remain the same. So what I mean by that is, if I do something like w by win comma c, this is not possible, because in my original input, I have total number of items equal to b into h multiplied by w multiplied by c. That many items we have. So we cannot reshape something of b times h times w times c, that many elements, into b times h times w times c divided by number of windows square. We can't do that, which means the dimensionality should match. So I have a here, windows here. So what is done is, we are simply saying that this h is now split into, let's say number of windows is 7. Now my height is split into 7 windows, where number of patches along each window will be, along the height will be h by win. So these two, if you multiply h divided by win, you get h back. If you multiply w divided by win multiplied by win, you get w back. So first is this viewing function. Second is, okay, let me also run this so that all these functions are available. Okay, this is functional. X comma, yeah, indentation is missing, but there is one more thing, one more step I have to do. Let's do one thing. Just don't forget about all the things that I showed you from the image, because in coding there are a few differences. So don't keep some of the things uh, confuse you. So let's follow this. So x dot view, I don't know what is missing here. Bracket was not closed. Where is it not closed? Okay, Windows C. Yeah, okay, now it's fine. Okay, now we have to do one more thing, which is I'm converting my image into Windows, which means I will have something, I need something like this, x equal to x dot permute. Okay, so I somehow have to combine batch dimension, then h by win, so b comma, so batch dimension is 0 dimension, then h by win is dimension number 1. Then this ideally I want to bring here, because think about what is the input that goes into my attention. The input is these three things combined, followed by certain number of windows, certain size of windows. So window size is 7 by 7. So what goes into my attention is 8 comma, according to the example we discussed, 8 comma 7 comma 7 comma 48. How do you get 8? 8 is nothing but your batch dimension, which was 2 multiplied by number of windows per image. Number of windows per image was 4. So the way you get that is, what is h by win multiplied by w by win? H by win is the total number of windows along the height. W by win is the total number of windows along the width. B multiplied by H by win multiplied by W by win will give you total number of windows in your entire batch. So you somehow want to bring these two items close to each other. This H by win and W by win, you should bring closer to B. So the second dimension, so 0, 1, 2, second dimension you want to move here, and third dimension you want to move into the second position. So 0, 1, 2, 0, 1, 3, then following by that 2, then 4 and 5 can remain as such. I will show you how this looks like. And 0, 1, 2, 3, 4, 5. Yeah, this is fine. X equal to x dot permute of that. Now what we want to do is we want to combine these three things. Meaning I want to combine B, H by win and W by win into one single dimension, and remaining things can remain as separate dimensions. So x equal to x dot reshape of, so I want to retain last three dimension, which will be windows, comma C. But the first dimension will be whatever results from these three. So I can just put -1. Python will automatically calculate what this number should be. But basically I am reshaping X. Let me actually show you a picture that will be much, much easier for you to visualize. Yeah, this is window partition. So the input that I'm sending into my window partition is the batch, then it has height, width, and channel. Now, I don't want the batch dimension to be preserved when I'm going into attention. What goes into attention should simply be the fact that I have 8, something like 8. I'm just putting actual numbers so that you can understand. I have 8 number of windows. Each window consists of 7 by 7 patches, and each patch is 48 dimension. So this is what I want. I just want 4 dimensions. Now, first what we did was to convert something like this into this. This is also 4 dimension, but here batch dimension is there, height of the image is there, width of the image is there. None of this I want, right? So what I instead want is size of the window along the width, along the height, and the dimensionality. So C needs to be preserved, of course. C is coming as such, but B, H, and W, I have to reshape it into some other format. So first step which I did was I divided H by win and W by win. So then I'll say if win is equal to the width of the window, then I'm saying along the height, I have these many windows. Then along the width, I have these many windows. But then since the number of items in the x dot shape and x dot view, I mean, in the x before and after this view function should be the same, I have to have this win and win because I'm dividing by win, which means I have to multiply by win. And then I'm rearranging the items such that B, H by win, and W by win comes close to each other, which is why 0th dimension, first dimension, and third dimension are now close to each other. 2, 4, 5 will be win, win, and C. So those will be the last three dimensions. And then I'm applying a reshape function where last three dimensions are preserved and remaining three are combined into one single dimension. So this -1 will take care of the default number, whatever that should be. Here, the default number would be B multiplied by H by win multiplied by H by width by win. So this is batches. Number of batches, number of images in each batch was 2. H by win is number of windows along the width. This was, if I remember correctly, this was in the example. I completely forgot. Number of items along the width was 2, 2, right? So this was 2 and this was also 2. So 2 times 2 times 2 resulting in 8. Then following that, you will have window dimension. This was 7. Window dimension, this was 7. Channel dimension, which was 48. So you will have 8, 7, 7, 48. According to this example, I'm not using these exact numbers, but that is how you finally get 8, 7, 7, 48. All right. So that is the window partition function. Now, window reverse function is relatively simple. First, you need to get the batch dimension back from your windows because now you don't have batch information here. Here, if you say B equal to, windows dot shape of 0, usually the 0th dimension is the batch, but this is not correct because what is the 0th dimension? 0th dimension is batch multiplied by H by window multiplied by W by window. So how do I get batch back? I simply have to divide by those two, right? I divide by the product of H by win and W by win. So if I divide the 0th dimension of my windows, which was the product of B and H by win and W by win, if I divide that by H by win and W by win, I get B back. So this is how I can get the batch back. Then X is equal to, now we have to reshape of, actually no, we can just view windows dot view. So first dimension should be batch, second should be H by win. Then we are now unpacking. So third will be W by win because we are unpacking B times H by win times W by win into 3 separate items. Following that, we had win, C. And then do the permutation once again. So now X equal to X dot permute. Now to get back this kind of a format, I have to once again bring with this guy to the third position and this guy to the fourth position. So I just say 0, 1 can remain as such. 2 and 3 will be flipped. So 3, 2, 4, 5. Okay, C is not defined. I also have to know what to see. But if you don't know what to see, just put this as -1. Python will automatically calculate what the last dimension should be. Because Python knows that if you multiply all these items multiplied by an unknown number, you have to get back whatever was the values of B times H times W times C. So Python can automatically, even if you don't explicitly mention one of these, Python knows what that value should be. That's pretty much it. X dot permute. And then you have to get this into the shape of your tokens. So you say h dot reshape of batch, comma, w, comma, height, comma, width, comma. I don't know the channel dimension because the channel dimension will depend on which transformer block you are in, which transformer stage you are in. If you are in stage 2, your channel dimension will be 2C. If you are in stage 4, it will be 8C. So I really don't know what exactly is the channel dimension. It depends on the stage. So I can simply put -1. So now I get back something in the nice format. So here I have B. H by W is now the number of patches along height and number of patches along width. -1 is it will automatically calculate what should be the channel dimension. So ideally, if, according to our example we follow, we can just say batch will be 2, H will be number of patches along the height, which was 14, right? W was also 14 and C was 48. So we get back what originally we wanted. Window reverse first line. Window reverse first line is basically this. Our X which was going in was B multiplied by H by win multiplied by W by win. That was the 0th dimension because that is what goes into the attention function. And then after this function, we will not immediately call this function because after performing Windows partition, we have to calculate the attention. Only then we will calculate Windows reverse function. But by the time some input is going into Windows reverse function, you don't know the batch size because by looking at this number 8, how do you know what is the batch size? How do you back calculate batch size from 8? 8 divided by total number of windows, total number of windows along the height divided by total number of windows along the width. That is your batch dimension. So 8 you have to divide by 2 and then again divide by 2. Only then you can get back batch. Just by looking at this 8, you don't know what's the batch dimension. So just like that, here, since you don't know the batch dimension, you take the 0th index item, then you divide by total number of windows along the height multiplied by total number of windows along the width to get back what was the batch size. In this case, it will be 8 divided by 2, basically 8 divided by 2 times 2, which is equal to 8 by 4 equal to 2. So 2 is the batch size. So that is how you get back batch size. All right. That is all about window partition and window reverse. I hope this should be fine. Then next part. Next part, we can code the class, window attention class for calculating attention inside or inside each window. So this we call as window attention. And of course, we have to pass nn.module so that it inherits properties from nn.module. Define underscore init, underscore bracket self, comma, bunch of things we'll have to pass, but we'll figure it out. Then super, so that we are calling the init constructor from the parent class, underscore. Then we need, first of all, the embedding dimension. So self.dim equal to dim, which means embedding dimension we have to pass. This we decide what that should be. Self.number of heads equal to this also we can pass. Then self.head underscore dimension equal to dim, self.dim divided by self.number of heads. Because total dimension divided by total number of heads will be the dimension of the token inside each head. And then self.scale. This is the 1 by square root of d thing, which we basically do query times key transpose divided by square root of d. So self.scale equal to whatever is the head dimension raised to minus 0.5, which will be 1 by square root of 5. And self.number of windows or the not number of windows, size of each window equal to win. And win we have to pass. So we are passing win number of heads and dimensionality of the input embedding. And then we can say self.query equal to nn.linear, because query we are projecting from dim comma dim, because what comes out of query is also dim. So we don't want to use the hidden dimension, which one, this head dimension explicitly we don't have to use it here. We could have used it if we wanted to calculate query key value separately, and then in the non-efficient way we could have said that for each query key value there are n number of heads, so calculate the context vector for each head, and then using a for loop combine them. We could have done that, but then all of that will be simplified if we simply say what the input that goes into the multi-head self-attention is dim, what comes out of multi-head attention after concatenation is also of the same dimension. Then self.key equal to the same thing. Now nn.linear, whatever comes after nn.linear, these are all learnable parameters. Then self.value is also equal to nn.dim. So basically key, query, and value are all three separate, the matrices corresponding to these three are three separate learnable matrices. Input dimension is dim, output dimension is also dim. Then after concatenation of the context vectors coming out from different heads, you project it into the same dimensional space, so that if you have head number 1, head number 2, head number 3, etc., you can perform appropriate mixing of whatever comes out of it. So you have a projection layer. This is usually very less discussed in the transformer architecture. Of course, we had discussed it, but in case you don't remember this projection, you concatenate all the items coming from head number 1, 2, 3, etc. But it's not, you don't want to preserve that 1, 2, 3, that order. So you have to perform some kind of mixing. So this projection layer will help you perform that kind of mixing. So it projects from d-dimensional space into d-dimensional space itself. This is not the multi-layer perceptron. Now comes a bit tricky part. Now we have to code, because is it enough for us to have query key value or query and key to calculate attention? We need two more things, right? We need relative position bias for calculating attention. We need one more thing, depending on window, what window we are. We need mask value. So these two things we need. So first, let us look at relative positional bias. So I'll just first show you the code, and then I'll show you with an example what the code is exactly doing. Then you will understand what we are doing. So in relative positional bias, we had said that if we have bunch of tokens in the form of patches. So let's say this is one window. This is not the image, one window. And inside this, I have patch number 1, patch number 2, 3, 4. All we need to do is, and then let's say I have another 2 patches. The delta x between these 2 patches is 2. The delta x between these 2 patches is also 2. So all we care about is if this is the query and this is the key, and if this is the query and this is the key. For this query key pair, delta x is equal to 2, delta y is equal to 0. For this query key pair, delta x is equal to 2, delta y is equal to 0. So in the last lecture, we discussed that if this is win and this is win, where win is equal to, let's say, 3. Okay. If this is 3, my delta x can go from -2 all the way till +2, because my query can be here, can be the third item, key can be the first item. So from 3 to go to 1, you have to do -2. So I have total how many unique values for delta x? I have 5 unique values for delta x, -2, -1, 0, 1, 2. Similarly, for delta y also, I have 5 unique values. So the total number of unique delta x, delta y pairs is 5 by 5, equal to 25. So the total number of learnable relative positional bias items is only 25 instead of 81. What is the logic of 81? I have 3 tokens along the height, 3 tokens along the width. Total number of tokens is 3 times 3 equal to 9. Every single token can be there will be query corresponding to every single token. There will be key corresponding to every single token. So total number of query key pairs is 9 times 9, which is 81, which means ideally I should have 81 position embedding terms or position bias terms. but I don't need 81 unique position bias terms. I only need 25 unique position bias terms because there are only 25 unique delta x comma delta y values. So now all we need to do is create a table of learnable bias where this is delta x, this is delta y, and this is the bij term. And for any given patch pair, calculate the delta x. So let's say delta x is -1 and delta y is 2. I just need to have a learnable position bias term here. Let's say 1.81. Like that, I'll have 1, 2, 3, etc. 25 items. And basically, actually, I will have 81 items because I have 81 token pairs, but only 25 items will be unique because for this query key pair and this query key pair, the relative position bias will be exactly the same because their delta x is 2, delta y is 0. So although I have 81 rows in this table, so this is like a table of learnable relative position bias, only 25 rows are unique. Remaining are repetitions, right? So we need to now construct this kind of a table. So now let's come back to our code, relative position bias term. So first is coordinates equal to torch.stack. I'll show you exactly what this code does. Then torch.meshGrid of torch.stack of torch.meshGrid of torch.aRange of windows, comma. So this will be a 2x2 grid. I will show you how this grid looks like. Then you will understand the code better. And I want my indexing to be ij, then that's it. So now I'll copy this and I will run it separately so that you can see. So now let's say my window value is 3. Now, what this means is I have 5 possible delta x values and 5 possible delta y values. And this coordinates will look something like this if I print. So delta x, delta y pairs. I have the 0th row, row number 1, row number 2. This is 0th column, first column, second column. Okay, it's not delta x, delta y value yet. That we are going to calculate. Then we flatten this. So coordinates flattened equal to coords dot flatten of 1. So after flattening, we can print it. So after flattening, it will look like this. So this is the row number 0, column number 0, row number 0, column 1, row 0, column 2. So you will have total 9 pairs here because totally you have 9 possible positions for, actually there will be total 81 pairs, but based on row and column index, you have either row number 0, row number 1, row number 2, or you have column number 0, column number 1, column number 2. And what is the 0, 1, 2? They are the indices of rows and columns of the patches inside your windows. Your window size is 3 by 3, which means totally you have 9 patches, and 9 patches are aligned as a grid of 3 by 3, which means totally there are 3 unique rows and 3 unique columns. Okay, so this is the flattened coordinates. Then we say relative coordinates is coordinates underscore flat of colon comma none minus, I'll show you what this code does. So now this is the array for storing my relative coordinates. And if I print this, it will look like this. So now look at the total number of items. I have 9 items along the row and 9 items along the column. And I have 2 such things. This is the first and this is the second. So now these are the all possible values of delta xy pairs. So delta xy pairs is this. So delta x is one of the delta xy pairs is 0, 0. Another delta xy pair is 0, -1. Another delta xy pair is 0, -2. So these are all the possible delta x values. These are all the possible delta y values. And if you pick the 0th item here and 0th item here, it is the delta xy pair. Like that, look at how many pairs are there. I have total 81 pairs. And I should have 81 pairs because not unique pairs though. I have total 81 query key value pairs, query key pairs. So my window size is 3 by 3, which means I have three tokens or three patches along the height, three patches along the width. So total number of tokens is 3 square equal to 9. So which means number of keys is equal to 9. Number of queries is equal to 9. So total number of query key pairs I can construct is 81, right? Which means I can totally construct 81 delta x comma delta y values. What are the delta x delta y values? The physical separation between query and key. Are they far from each other or are they close to each other? Now, out of these 81 delta x comma delta y pairs, everything will not be unique. That's what we're saying. You will have only 21 such pairs. So, for example, here you see the delta x delta y value is 0, 0. But now look at this item. This is 0, 0. So many delta x delta y pairs will be repeating because the total possible delta x delta y pairs you can have is the maximum value for delta x possible is +2 because you have only 3 windows. So +2 will be, this can be query and this can be key or vice versa. So this is like at position number 0. This is at position number 2. So the distance between those delta x is 2. Minimum value possible is -2. The range of possible delta x values are 5. -2, -1, 0, 1, 2. Similarly, range of unique delta y values possible are 5. So totally unique delta x delta y values will be 25. Okay, so if you count all the delta x 81 delta x delta y values as per this, you will see that only 25 of them are unique. Okay, and then we say rel equal to rel dot permute of 1 comma 2 comma 0, and I'll show you what this does. This simply rearranges the pairs in this way. So now you have pairs close to each other, 0, 0. So this is delta x delta y. This is another delta x delta y. This is another delta x delta y. So now you have all the delta x delta y pairs. Then you say rel of comma 0 is equal to, so of 0 means this is the delta x value is equal to that plus number of windows minus 1. I'll tell you why exactly this is done. So you are adding some constant to your delta x values, and then you are adding some constant equal to this plus some constant. So the reason why this is done is my original range of delta x values were from -2 to +2. If window equal to 3, what is window minus 1? It will be 2. So what happens if I add a constant value of 2 to all possible delta x values? My delta x values will now range from what to what? My new range of delta x values will be from 0 to 4. So basically, this is just to avoid negative numbers in the relative, because I don't care about the absolute value. I just want unique set of numbers. So my relative positioning will be 0 to 4. So that is done for delta x and delta y. Now one more thing is done, which is this comma 0 equal to whatever is that number multiplied by 2 times window minus 1. So here what I'm doing is the x values. So these are delta x values. These are delta y values. So I added a constant number called 2 to delta x. I added a constant number called again 2 for delta y. So delta x values range were from -2 to 2. Now it will become from 0 to 4. Delta y will also become 0 to 4. Now I'm multiplying every single delta x value with 2 times window minus 1. 2 times window minus 1 is 2 times 3, which is 6. 6 minus 1 is 5. So now every single delta x value I have multiplied by 5. So what will be now the new range of delta x values? it will be from 0 to 20. Very good. Because my original range was from -2 to +2. That I shifted to be 0 to 4. Now I am scaling it such that it will be from 0 to 20. I'll tell you why this is done. So first, let me show you when I print the value of relative, you should understand what is the cool thing about this. The cool thing about this is, let me do one more thing. Rel of 0 equal to, okay, this is fine. And now index equal to rel dot sum of -1, and maybe I can print index. Now, what I have done is a range of delta x values will be now 0 to 20. Range of delta y values will be from 0 to 4. And I'm saying that I'm adding the delta x and delta y value to get some numbers. And look at those numbers. The number that is resulting, I have now 81 positions, right? I have 9 tokens total as query, 9 as total as key, which means I have total 81 unique, not unique, I have total 81 query key value pairs. And somehow I should be able to say, if I were to pick query key pair from index 0, 0, it has a index of, let's say, 1. Then if I pick another query key pair from somewhere here, let me repeat by drawing a new picture. My goal is this. I should be able to just tell with one number that if my query key value pair query is this and key is also this, or if query is this and key is also this, then when I'm looking at my table, I should look at ideally the same item in the table, right? So I'm basically converting my query key pair into one single index. So the index corresponding to this, if this is 3, index corresponding to this will also be 3. Now let me ask you, what exactly should be the index? So what we did was, this was 3 and this was 3. Now let me just delete this. Now assume that my query is this item, key is also that item. Okay. Now, what was the original delta x and delta y in this case? Delta x, delta y was 0, 0, correct? After shifting delta x, what happened to delta x? We shifted the delta x by window -1, correct? Window -1, which means 0 will become 2. So this will become 2, 0 after only shifting delta x. Now, after shifting delta y, what will this become? 2, 2, correct? Because delta x and delta y both we shifted by 2. Now we did scaling for the delta x. We scaled the delta x by a factor of what? 2 times window -1, which is 2 times 3 -1, 5. So this will become 10, 2. So now my new, after scaling and shifting, after shifting and scaling, my delta x new, delta y new will become 10, 2. Now what I'm saying is, my index will be simply the sum of these two. So my index will be 12. So now look at this. What does 12 mean? If the index is 12, it means query and key have 0 shift relative to each other. They are at the exact same position. Correct? Now, let's take this example. Let's say my query was here and key was here. What is the delta x in this case? Delta x was originally 1, delta y was 0. Delta x I will scale, I will shift by 2. So 1, 0 will become 3, 2 after delta y shift. Then I will scale by multiplying with 5. So this will become 15, 2. So now what is the index corresponding to this? 15 plus 2 equal to 17. So these two pairs will have an index of 17. These two pairs will also have an index of 17. Every pair that with a delta x shift of 1 will have a pair will have an index value called 17. Every query key pair with no shift, meaning query key at the same place, will have an index of 12. What about index of 0? Which pair will have an index of 0? I don't know if any will have a 0, but they will. Please don't assume that just because index is equal to 0, don't assume that delta x comma delta y equal to 0. That's not the case. The original delta x delta y was 0, but then delta x we shifted, delta y we shifted. This is just to create unique indices. So I'll just print the index and just have a look at this. So these are the printed indices. Now look at all these numbers. What does this mean? This means these are all the different query key pairs where query and key are the same index. So those 9 items are basically, this is the query, this is the key. Similarly, this is the query, this is the key. This is the query, this is the key. Like that, how many items you have? 9 items you have, because it's 3 by 3. So if query is the item number 1 and key is also the item number 1, meaning the index of query is corresponding to token number 1, key is also corresponding to token number 1. Similarly, query is corresponding to token 2, key is corresponding to 2. So you have such 9 items. All those 9 items will have the index of 12. Something will have index of 0 if they are farthest apart along, I would say, the probably the diagonal. Maybe we can calculate it. So let's say delta x delta y was 2 comma 2. This is the farthest item, right? Delta x is 2, delta y is also 2. So after shifting, this will become 4 comma 4. After scaling, it will become 20 comma 4. So this will index will become 24. So one of the farthest items will be 24. Is that correct? See, 24 is the farthest item. Now let's look at the other farthest item, minus 2 comma 2 perhaps. They are also far away. So minus 2, after shifting, minus 2 comma 2 will become 0 comma 4. And then after scaling, this will become 0 comma 4 itself. Then after adding, it will be 4. So this is not the 0 item. How about minus 2 comma minus 2? If it is minus 2, after shifting, this will become 0 comma 0. After scaling, it will remain as 0 comma 0. And then index will be 0 plus 1, 0 plus 0 equal to 0. Yeah. So basically, this item corresponds to the index where query is at the position 0 comma 0 and key is at the position 2 comma 2. So they are farthest away from each other. Delta x is 2, delta y is 2. This 0 corresponds to the item where query is at 2 comma 2 and key is at 0 comma 0. So basically, this is now the table of indices corresponding to delta x, delta y values. I mean, this is one small part of our code. I'm spending too much time, but I hope you understand. It's basically constructing a table of unique indices. So let me just copy this. 25 unique indices. I should not say unique, because when I say unique, you will think there are 81 unique indices. That's not the case. There are 25 unique indices. Okay. Then we call this function called register buffer. So the register buffer is defined in nn.module. And here we say position underscore index. So we store it in this variable. Is basically this index. We will use it later, not right now. Then self dot relative bias. So this is where we define the relative bias, relative position bias term. Self dot relative bias is equal to, this should be obviously a learnable parameter. So nn dot parameter of torch dot zeros. And how many position bias should I have? I should have a range of values from 2 times win minus 1, comma 2 times win minus 1, which is 3 times Windows is 3. So total, my spelling mistake. And then I need position bias separately for different heads. So number underscore heads. I'm sure there is some syntax error. So there should be, this is a 2D array. Okay. 2 times win minus 1, comma 2 times win minus 1. And so total number of values should be, its range should be from 0 to 0 to 24, basically. So 2 times win minus 1 is 2 times 3, 6, 6 minus 1, 5. 2 times 6 minus 1, 5, 5 times 5, 25, which means the range will be from 0 to 24. Okay, so this is fine. I think I'm missing one bracket somewhere. I'll see. I think torch.zeros of this, and yeah, number of heads should be here. All right. So that is the relative bias. So now we have relative bias. One thing we have not defined yet is the mask. So mask we should define a little bit, we'll define a little bit later. So that is the window attention class. And now we can define the forward pass function. So define forward, and into this usually we pass self comma x. And if anything else is passed, we can pass that also. So here actually we can pass, mask, and mask by default, there is no mask, which means none. And this is only for regular window. Regular window does not have any mask. Shifted window has mask. And then we say batch underscore, which means we don't know what is the batch dimension. So we just say the calculated batch dimension, comma n, comma c is equal to x dot shape. So this is what comes into the x is what is there available in the window attention. And then we say query is equal to self dot q of x. Key is equal to self dot q of self dot key of x, and same for value. And now we can take the dot product. So q is equal to q times scale, which is 1 by square root of d, q times self dot scale, because we scale the queries before multiplying with the transpose of key, and the attention before adding the relative position bias and before adding the mask term is q matrix multiplication followed by k dot transpose. And when we are transposing the last two dimensions. So -1 is the last dimension, -2 is the second last dimension. So this we are transposing. Basically, we are doing k dot t. The only thing is k also has batch dimension. So just to make sure that this can be, I think, k dot transpose of 1, 2 also. This can be written as 1, 2, which means it will take the first dimension number 1 and dimension number 2. But ideally, what we are trying to transpose is the last two dimensions, which means last dimension is -1, second last dimension is -2. And then we calculate the relative position bias. So RB equal to self dot rel underscore bias. And this is for a certain position. So self dot position underscore index, which we have passed here into the function, and dot view of -1. Basically, all the 0 to 5, all the list of values will be seen as one single table. When you say -1, we are basically looking at it from just one dimension. Let's not go into the detail. If you just simply print this, you will see what the position index dot view does. Then dot view of n comma -1. I'll explain after a little bit, after we proceed a little bit, why exactly are we expanding it into n comma -1. Then attention equal to attention plus relative position bias, which is RB, dot permute of 2, 0, 1 dot unsqueeze of 0. Let me show you why exactly are we doing these things. Maybe I can do it after masking is also added. So just understand that here that this is just to take care of dimension, all these indices thing. I'll explain that in a little bit. But broadly understand what we are doing. We have the query key value. Then to add to that, we add the relative position bias. Now we have to add the mask. So if mask, basically if mask is none, then we don't have to add anything. If there is no mask, we add nothing. But if mask is not none, by default, we are passing mask equal to none. But if mask was not none, which will happen in the case of shifted window, the number of windows is equal to mask dot shape of 0. So these are the total number of windows. And then we say attention is equal to attention dot view of whatever was this B divided by number of windows, comma, number of windows. So whenever we divide by this, if we are viewing, we have to multiply with the same thing, which is why when you divide by number of windows, you add extra dimension, comma, number of windows. I'll explain this part also in a bit. Self dot number of heads, comma, m, comma, n. Then attention is equal to, so now attention is in the right dimensionality, attention plus mask dot unsqueeze of 1 dot unsqueeze of 0. And then attention, I know that there are a lot of matrix manipulations here, but let's go through that once we write the code so that coding is not delayed. I just want to make sure the code works at the end of the day, comma, n, comma, n. So now we have the attention with the bias term added, and mask, if it is there, mask term also added. After this, what do we usually do? We take softmax, right? So then attention, n is the total number of tokens. N by n is the total number of tokens in each window. I'll come to that. Then attention equal to attention dot softmax and that too along the column dimension. So dimension equal to -1. So we take the softmax, and then after this we multiply with value matrix. So then we say the final output we have is attention matrix multiplication with value. But whatever we get, we have to take a transpose. I'll say exactly why we are taking the transpose. 1, 2 dot reshape of batch, n, c. Then we say output equal to self dot. So we have to now do this projection, which I mentioned earlier. After calculating the attention, we have to use this projection layer to mix different outputs from different heads. So self dot project of out, then return out. So this is the part where attention is calculated. Now let me show you the details of these lines, because I'm pretty sure several things are unclear here. Before that, let me just run this to ensure that there is no syntax issue or anything. Okay, this is running. Okay. Okay, this you understood. Window partition you understood. Window reverse also we explained. Window partition is done just before attention. Window reverse is done just after attention. Now what we are discussing is attention. So in attention, these are the things we did, right? We have query key values. We have relative position bias, which is the Bij term. We have the attention mask Mij term. Then we first calculate Q by square root of D. Then we multiply it with the transpose of key. Then we add relative bias. Then if mask is there, we add that. We apply softmax. Then the final context vector matrix is softmax of attention multiplied by the value vector. This is conceptually, this is what we are doing. But code wise, okay, window reverse part we already discussed. But yeah, let's quickly go through relative position bias. Let's say my window is 3 by 3. I have totally 9 tokens, which means I have 9 queries and 9 keys. So total query key pairs are 81. This is very clear. So the range of values of delta x will be from -2 to 2, which means there are totally 5 possible delta x, delta y values, which means total 25 unique delta x, delta y pairs. So this we have to now construct into a sort of like a lookup table. So in this lookup table, what we are doing is we are constructing indices, which is just one number. That number ranges from 0 to 24. where 0 means it will mean a particular delta x delta y value. 24 means it will be a particular delta x delta y value. Here we discussed that 24 is resulting from plus 2 comma plus 2 delta x delta y. 0 is resulting from minus 2 comma minus 2 delta x delta y, and 0 comma 0 delta x delta y value was resulting in what index? What was the index corresponding to this? 12. All the columns, all the diagonal values were 12. Okay. So this is the position bias. Then what we did was we had a line like this, self dot relative bias. So in the code, this was the line. RB equal to self dot relative bias of, then we were calling the items in the table. Then we were kind of adding more dimensions to it. So what we are doing is position index. You might have seen this was n by n, which was 25 by 25. Correct. This was the table size, because table size was 2 into window minus 1 multiplied by 2 into window minus 1. These many items were there. So this was, window was 3. So 6 minus 1, 5, 5 by 5. So it was 5 comma 5. 25 comma 25, if I'm not wrong. 25, sorry, 5 comma 5. Then what we are doing is we are creating the position index as a list of values ranging from 0 to n by n, 0 to, so totally 25 indices ranging from 0 to 24. So position index dot view of -1 will ensure that if you had two-dimensional grid of values ranging from 0 to 4 and 0 to 4, you will be converting that into an index consisting of 25 items, a one-dimensional array consisting of 25 items. Those 25 items will correspond to the 25 relative position bias items. Then what we have to do is we actually have multi-head self-attention, not single head. And if you remember the part where we defined this relative bias, there was a comma number of heads. So comma number of heads means for each head, we have separate relative position bias learnable parameter. So for example, if my window size is 3 by 3, right, I have totally, instead of 81, I have 25 unique position bias values. But if I have 4 such attention heads, I have to learn 25 for attention head number 1, 25 for attention head number 2, 25 for attention head number 3, and so for 4. So for each head, I have to learn it separately. So here what we are doing is self-relative bias is basically, by default, it was 25 comma number of heads. And what we want to do is we want to go from, if I had 25 items that are unique in a table, I actually have 81 items because I have 9 queries and 9 keys. But then like this, I need one for each head. So I need one table like this for head number 1. I need one table like this for head number 2. But within each head and within each table, only 25 items will be unique. So what we are at the end of the day doing is we are converting this relative bias into something like n by n for each head. So n by n will be 5 comma 5, and it will repeat for each head. So total number of learnable parameters will be 5 times 5 times number of heads, basically. So if number of heads is 3, I will be learning 75 unique items. So in short, that is what we are doing. And then finally, what we get out of this, attention equal to attention dot rb dot permute of 201. So 201 means the original dimension was, this is 0 dimension, this is first dimension, this is second dimension. We switch it like that, like this, in such a way that you go from n comma heads, you go to heads comma n, and then you add a batch dimension also. So then you try to add a batch dimension also. So now what this means is, you, for every batch, so you have 2 batches, let's say, for every batch, you have n number of heads. And for every head, you have a lookup table, which has n by n unique items. And these items will be now be added with the self attention. So that is what that is happening at the end of the day. If I end up spending a lot of time on this line, it will take me another 1.5 hours to code the rest of the code. But let's understand this from a broader level. From a broader level, we are simply trying to add mask value and relative bias value to the query key dot product, scaled query key dot product. From a slightly zoomed in perspective, the reason why we are doing this unsqueeze or this view operation is just to make sure that the dimensionality when we are performing addition and multiplication are all matching, because we have batch dimension, we have numbers associated with number of heads. So all the dimensionality should match each other when we are adding or multiplying these matrices, which is the reason why we are often doing a permutation of the indices or performing this unsqueeze. Unsqueeze meaning you add one extra dimension. In mask also, we are doing, okay, we have to calculate normal self-attention for each head. Exactly. So self-attention will be, self-attention is already calculated over here. Attention is equal to query times key transpose. And this is done for different heads separately. And then at the end, the output is concatenated. PyTorch will take care of it. We don't have to do it because we did not define the query weight matrix as something of dimensionality head dimension. Like usually, if we were implementing simplified self-attention, we would have said that the dimensionality in the query space is head dimension, dimensionality in the key space is head dimension, and in the value space is also head dimension. For each head, like that, we will have num heads. So ideally, we'll have to calculate for each head context vector matrix and then manually concatenate it using for loop. So, but then I hope you remember from one of our earlier lectures that we can do it in a much more efficient way by just considering one query matrix, one key matrix, one query weights matrix, one key weights matrix, and one value weights matrix. That is basically what is being done here. So query key value being in multi-head attention is automatically taken care of here. And then after you have query key values, you calculate first the attention scores. Then to the attention scores, you add the relative bias. Then optionally, you add the mask value. If you are in the shifted window, if you are in the regular window, your mask value will be none, which means this entire if condition will not be applicable. Then you multiply with value to get the final output. I will come back to this, why we are doing this unsqueezing just to match the dimension in a little bit. But what I will do is I will anyway share I have written detailed reasoning why we are doing a certain unsqueezing operation here. So I recommend you to go through it, but let's just go ahead with the coding part. And if we have time a little bit, we will come back to the this unsqueezing operation. It's actually very simple, but let's rather spend time on coding the next part. Okay, so now we have what? We have the attention defined. So now after this, we need to define the Swin block. So this, let me delete. This is just for the example purpose. We don't need this anymore. Coding Swin block. Now class Swin block of nn.module define underscore underscore init underscore underscore, then we pass self. Then we have to pass bunch of things here, but we'll see that. Then super init. So we are initiating the init constructor in the parent self.dim equal to dim. So we have to pass the dimension, embedding dimension here. Then self.resolution. So here we are passing the image resolution. The only reason why that is done is different stage. Depending on which stage the Swin block is, the resolution is different. I hope you remember that from here. So in the stage number 2, the resolution was h/4 h/4 going input resolution. Sorry, h/8 h/8. In stage number 1, it was h/4 h/4. So the resolution truly depends on which stage of the Swin transformer we are at. So Swin transformer block needs to know what is the resolution of the input. So that is why we are defining this self.res equal to res. So we pass resolution here. Then self.number of windows, that also passed here. Then self.shift. So shift is the amount by which we are adding the shift. this, I hope you remember, the shift value was m by 2, where m is the width of the window, or integerized m by 2. So if m is, let's say, window size is 7, the shifting will happen not by 3.5. There is no 3.5 patches. Shifting will happen by 3. So we have to pass the shift value. For regular window, shift value will be equal to what? What will be the value of this variable for regular window? 0. For regular window, there is no shifting. For shifted window, the value will be whatever is the window size divided by 2. So if window size is 7, divided by 2 is 3.5. Rounding down to the integer is 3. Then inside the Swin block, look at what all things are there. You have a multi-head self-attention, you have 2-layer normalization and 1 multi-layer perceptron and residual connection, right? Same as the normal transformer. So let's define 2-layer normalization. So self.norm1 is equal to layer norm of, layer norm should be along what dimension? What should I pass here for both layer norm actually? Self.norm2 equal to layer norm of what? I'm normalizing along embedding dimension. So every single, I just need to mention the embedding dimension. That's it. So first will be dim. This also is dim. But here it should be nn dot layer norm, because it's inherited from nn module dot nn dot module. So those are the 2-layer norms, but let me not confuse you by writing them together because they are not applied together. So after the first layer norm, I have my attention. So self dot attention equal to, here is where we define, where we use this thing which we have defined, window attention. So we copy paste that window attention off, and into the window attention, I have to pass bunch of things: dimension, number of heads, and win. So dimension, number of heads we have not defined yet. So that perhaps we can define here as h heads, and then heads we can directly pass here. And win is the window size. So these were the 3 things we needed to pass. Then after this comes the self layer norm 2. So layer normalization 1, attention, then layer normalization 2, and followed by this multi-layer perceptron, self dot MLP. So MLP will be nn dot sequential. Then first item will be nn dot linear, and it is projecting from dimension to what? Usually what is done, if you remember from the transformer, we project it to a 4x dimensional space, right? 4 times dimension. Followed by that, we have an activation function, which is JLU. We can use RayLu also, does not matter. Then you project it back from 4x dimensional space into your original dimensionality. So this is multi-layer perceptron. Okay. And depending on whether your Swin block is with or without shifting, you have to define a few things. So firstly, h comma w equal to resolution, which means resolution we can pass here. Actually, resolution we are already passing here. So this can be called as res. Then h comma w equal to res. Then if shift is greater than 0, meaning if this is not a regular window, if this is a shifted window, only then we have to define a mask. So then self dot mask equal to, then here we have to define like a create mask function, but let me first write it, self dot create underscore mask of, we have h patches along the width, along the height, along the width, number of windows, and what is the quantity of the shift. So this we have to pass into the mask. This we are yet to define, but I will define that soon. Else self dot mask equal to what? What should be self dot mask? None. Because if shifting is not there, if it's a regular window, we don't have any mask. So default value of mask will be none. Now we can define the define this create mask function. So define create underscore mask, into which we pass self, comma, rest of these things. Oh yeah, thank you so much. Yes. These minor things will cause issue, and we'll have to spend a lot of time figuring this out. Where is the issue? Okay, and image mask equal to torch dot zeros of so we don't need we just need 4 dimensions, h comma w comma 1. This is okay if this is 1. In broadcasting in Python, there is something called broadcasting. If we are adding mask to something, and if that something has a batch dimension of b and channel dimension of c, automatically Python will broadcast this into the rest of the dimension. So we don't have to explicitly mention the value here. Then count equal to 0. I'll show you why this count is done. Now we need some we need some indices for our window ID. Basically, we said window ID for patches belonging to the ID of the patches, if they are belonging to the same window, should be the same. So what we are going to do now is we are creating something called slice. So for h in, so we have totally 3 slices. So h in slice of 0 comma minus shift, or no, not minus shift, minus win. I'll explain what this is doing, comma minus win comma minus shift. So that is in h. And so basically I have 3 patches along height and 3 windows along height and 3 windows along width. So w in 0 comma win, I think this is fine. Count or image mask equal to image mask of comma h comma w comma this equal to count, and then count plus equal to 1. So what is done here is pretty simple. So basically what we are doing is we have 3 vertical slices and 3 horizontal slices when we are shifting. Something that looks like this. There is this corner items, there is this corner item, this item, these items. So originally there were 2 by 2, but after shifting we'll have 3 by 3, and then we have to just mention ID. So totally we have to go through 3 items along the row and 3 items along the column. So basically there are 3 vertical slices and 3 horizontal slices. So this is the first vertical slice, this is the second vertical slice, and this is the third vertical slice. Similarly, this is the first horizontal slice, second horizontal slice, and third horizontal slice. Now, depending on which slice you are in, you can mention the ID. Then count. So basically you maintain a variable called count, and the image mask value for that h comma w will be the count value. We can print this to see how it looks. Then mask equal to window. So mask also we have to pass through window partition, because mask is added inside the attention. So inside the attention, by the time your inputs reach the attention, you had already passed the inputs through window partition. And that is the reason why you could process it on a window basis inside the attention. So same thing you have to apply for mask. So we apply window partition for mask also. Window partition you had defined here, window partition and reverse partition, window reverse, window partition and window reverse. We have not touched window reverse yet. Of img mask comma windows, then mask equal to mask dot view. This is just to adjust the dimensionality, -1 comma win times win. So here again there is bunch of dimensionality maneuvering that we have to do to make sure that we are this is not correct. We are getting correct dimension before we add the mask to the query key dot product. Mask dot mask fill where mask not equal to 0. And basically, if the mask is not null, we said that we usually add something like minus infinity, a huge number as the mask value. This, if you remember, we did. Why did we say that the value of mask ij is minus infinity if there is mask present? The reason is we want the softmax value to go to 0 if the ID of the window was different for two different patches, because two different patches from two different windows should not have attention score with each other. Their attention score should be 0 or a very small number. Here we can define it to be like minus 10,000 or some big number, so that the softmax value goes to a very, very small number. Let's keep it a floating point. And then we simply return mask. So we are still in the mask function. So from the mask function, we return this mask value. And now we can define the forward pass. Define forward of self comma x. Then you have batch comma L is the total number of length of tokens. B comma L comma C is the channel equal to x dot shape. Then height and width are okay. Something is missing. Define okay. Indentation was wrong. So h comma w equal to self dot resolution, because resolution we were passing in here. Then okay, so now we are in the window the regular self attention transformer block or shifted window self attention transformer block. So we have the inputs coming in. We have to store the residual. So residual equal to x, and we have to add it later. Then x equal to, first we do the layer normalization. So self dot norm 1 of x. We had defined norm 1 here. Then after layer normalization, we make it pass through attention. So x equal to or one more thing we have to do. Yeah, norm 1 of x, and x equal to x dot view of batch hwc. Now, are we ready to call the attention, or are we missing something? Before the attention, we have to do window partition, right? Then only we can call the attention, and after attention, we do window reverse. So then we can say if self dot shift not equal to 0 or greater than 0, meaning if we have a shifted window rather than a regular window, then we say x equal to torch dot roll. So this function allows us to perform that rolling operation, the cyclic rolling. Shifts equal to minus self dot shift comma minus self dot shift. So we are shifting by m by 2, by minus 3 to the left hand side direction, minus 3 to the top direction. I mean 3 by 3 points to the left, 3 to the top. And dimensions along which the shift happens is the first and second dimension, because first and second dimension are the height and width dimension. And so if self dot shift is greater than 0, then we do this cyclic rolling operation. And then we have to do the window partition. Win x equal to window underscore partition. This function was defined earlier. Into this we pass x comma self dot window size, and whatever comes out of window partition, we arrange it in a dimensionality like this. Comma C. Then once we do the window partition, we can do the attention output equal to something, and then we have to do again window rolling. So then we can say window reverse underscore reverse, and into this we have to pass a few things. And after window reverse, we have to unroll. So whatever rolling we did, we have to unroll. This is called reverse cyclic reverse shifting. So for that, all we need to do is we shift it back, which means this minus we replace with plus. And so this we are yet to fill. Okay, we'll come to this. So attention dot out is self dot. What was the name? Self dot attention, ATTN of window underscore x. So whatever we get out after window partition, we pass that, and then mask we have to pass mask. But one thing we have to do is whatever CPU or GPU we were using, same the mask also we should convert to this. So whatever device mask was using, same device attention calculation should also use. So self dot to device dot device dot x dot device. And but this we need to do only if there is a mask, otherwise we don't have to do. So if self dot mask is not none, else none. So basically what we are doing is we are passing the mask as not none if there is a mask. Otherwise, if mask is none, we are just simply passing none. Okay, then x equal to window reverse. Into window reverse, we pass whatever output we get from attention. So after whatever input output comes from window partition, we pass to attention. Whatever output comes out of attention, we pass to window reverse. Attention output, comma self dot win, comma height, comma w. These were the arguments to the window reverse function. And then this is the reverse cyclic shift. And then we have to add the residual. So after the multi-head attention, we have to add the residual. So x equal to x plus residual, or residual plus x dot view of bash comma L is the number of tokens comma C. And then we are ready to do the one more layer of self normalization, x equal to self dot norm2 of x. So this is the second layer normalization. Actually, I can store one more residual here. So residual 2 equal to x. And then I say x equal to self dot MLP of x. And then after MLP, I just say x equal to x plus residual 2. So now this is the part where the second layer normalization MLP and residual comes. I'm just storing the residual here. This is the part where, okay, let me just delete some space so that so this whole thing is the part where we do layer normalization number 1. We perform cyclic shifting if we are having a positive shift. Then we perform window partition so that we can perform attention within each window. Then we calculate the attention. Then we do window reverse so that the batch dimensionality which was lost during the attention calculation is coming back due to window reverse. And then if cyclic shifting we had applied, we apply a reverse shifting so that now we don't have a shift anymore. And then we add the residual. So this will complete the first part of the first half of the transformer block, this from here till here. And then we have one more layer normalization, MLP and residual. So that is layer normalization number 2, multi-layer perceptron followed by residual number 2. And then we can simply output this, return X. So that is the Swin block. Now a bit more is there to write, is class patch merging. So patch merging, if you remember, it is this guy where the dimensionality, spatial dimensionality was becoming half and half. The channel dimensionality was becoming 2x. So class patch merging nn dot module, then define underscore underscore init. Actually, let me try running the previous class just to make sure it works. Okay. Then self dot dimension, embedding dimension equal to embedding dimension. We have to pass that. Now, first is we reduce the spatial dimensionality by combining 4 neighboring patches. So self dot reduction equal to nn dot linear of 4x dimension. So first we will have a 4x dimensional thing. From that we'll go to 2x dimensional. And bias, yeah, bias can be false. There is no bias we are adding. Then in that layer, there is one layer normalization. We have not discussed this in the lecture, but a layer normalization is added. 4x dim. Then forward pass. So this is a relatively straightforward function. Self comma x comma height comma width. Batch L C. L is the total number of tokens, is equal to x dot shape. Then x equal to x dot view batch height width channels. Now we have to extract 4 patches and then concatenate them along the channel dimension. So patch number 0, patch number 1, patch number 2, and patch number 4. So these 4 patches we have to do, and we have to extract, and then after extracting we can simply reshape that into a dimensionality like batch comma -1, whatever that dimension is, comma c. I can do that for all the 4 patches. And then simply concatenate them along the channel dimension. We are yet to do this extraction, but that is just one line of code. Then we say x equal to torch dot concatenate. And here x0, x1, x2, comma x3, comma, this is concatenated along the last dimension, which is the channel dimension. And then we apply layer normalization, x equal to self dot norm of x. So this layer normalization comes inside the patch merging just before you get it out so that you can pass it to the transformer block. And x equal to, in fact, just before the reduction. So reduction we had defined here. This is where you go from 4x dimensional to 2x dimensional, because 4x dimension results from this patch concatenation, and 2x dimension resulting from a linear projection. Reduction of x, and then return. You are returning now x. You are returning the resolution. Your resolution will become half h by 2 and w by 2. And here we have to extract the 4 patches. So x of 2, then 2, and then this should be 1 to 2. Yeah, I think this will work. Basically, we are extracting 4. Yeah, I think this is correct. Let's run this and see if there is any error. We'll fix this. But basically, this extract is 4 patches, concatenates them along the channel dimension. After concatenating, we do one layer of layer normalization and then reduce it into 4x dimension to 2x dimension. So you go from 4x to 2x through a linear projection. Okay, that is patch embedding and seems to be working fine. I think now we are pretty much done. Now the last thing is we just have to define the full Swin transformer multiple stages, but we won't be writing 4 stages. 4 stages too much. We'll just write maybe 2 stages. So class 2-stage Swin MNIST for MNIST. nn.module and define init dot underscore init and self and a few other things. So first is we have to perform patch embedding. So we'll come to that. So first embedding dimension. So self dot embedding dimension equal to embed underscore dim, and we have to pass this. Then second is self dot patch underscore embed equal to, and this was how did we do this? Using nn.con2d. And input channels was 1, output was whatever was the embedding dimension. Initially we were doing one step we are skipping here. In actual transformer, Swin transformer, we first go from 1 to 48, and then from 48 you have a linear projection to whatever C dimension it's. We are skipping that step. Then kernel size is equal to 2 because it's MNIST and we don't need big patches. Stride equal to 2. So this is the patching. And then initial resolution after patching will be simply 14 by 14. Now we can define stage 1 of the Swin transformer and stage 2. Stage 3 and 4 we will skip because we can't divide the spatial resolution too much anyway for MNIST. Then self dot stage underscore 1 or stage 1 blocks equal to nn dot sequential. So what all do we need here? We need in each stage of the Swin, we have 2 Swin blocks, right? So we have to call this class Swin block class. And that too we have to do twice. So we have to call this twice, but there is some small difference. To this, the shift will be 0 because this is regular window. To this, the shift will be 7 if our size is window size is 7, shift will be 3. So to this, the shift will be 3. But then there are a few more inputs we need. First is self dot stage 1 shift equal to 0, embedding dimension. So that we'll pass to both. Then number of heads, that we'll pass to both. And heads we should pass here. And the window size equal to win. So we have to pass windows here. Then shift. Now we can also define the values, and there is number of classes also. So for MNIST it is 10. So we can just set default value. Window size, let's keep it 7. Heads, let's keep it maybe 3. And embedding dimension should be a multiple of 3, of course. So let's keep it 48 itself. Okay, these are the numbers. And then stage 1, you have Swin block. So in stage one, you must note that there is no patch merging. In stage one, you simply have this linear embedding. In stage two, you have patch merging. In stage one, there is no patch merging because before you are for the first time you are getting the patches. Merging happens only after stage one onwards. So that is stage one. In stage two, you copy paste almost the same thing, except stage two resolution. Stage two resolution equal to initial resolution, whatever was the initial resolution of 0 by 2, because by the time you pass the first stage, the resolution would have reduced by half, which will be 7 by 7. Then stage 2 blocks is nn dot sequential. But before that, we have to also do patch merging. So self dot patch underscore merge equal to patch merging class. Embedding dimension and merged dimension equal to whatever was embedding dimension multiplied by 2. So the dimensionality after stage 1 to stage 2 goes from C to 2C. So embedding dimension multiplies by 2 after each stage. The spatial dimension divides by 2 after each stage. Okay, so that is almost it. We are pretty much ready. So we have to now pass the, okay, we forgot to pass the initial resolution. So initial resolution, because resolution is expected as one of the inputs in the Swin block as the variable name under res. Then we pass stage 2 res here. And I think that's pretty much it. And one more thing. Yeah, so window. So here there is one small thing you need to note. So if I divide win equal to win by 2, and this is win by 2, shift is equal to 0. And here shift equal to whatever was the window size divided by 4. This causes a bit of dimensionality issue, but we'll fix this at the end. Okay, so just keep a note of this. This will cause an issue because MNIST is a very small resolution image. Then self dot layer norm of equal to nn dot layer norm, and that happens along whatever is the merge dimension. And self dot fully connected layer. So now we are out of the Swin transformers. After stage 2, we don't have transformer anymore. We just now want to perform global average pooling, and we also want to have a fully connected layer going from merge dimension to 10 classes. So self dot fully connected equal to nn dot linear from merge dimension to whatever is the number of classes, num underscore classes. So this is where the classification happens. Now we are ready to define the forward pass. Self, yeah, we did not define yet because that we can do inside this forward function. Then x equal to self dot patch underscore embed of x. So this patch embedding, once we have the patch embedding, we want to know the batch height, width, batch channel height and width equal to x dot shape. Then x equal to x dot flatten of 2 dot transpose of 1 comma 2. So this is where we are flattening this whatever patches we get after con2d operation, we are flattening it here. Then those flattened patches, the total number of tokens or patches is h multiplied by w. Then x equal to self dot stage 1. So this is where the stage 1 of the Swin transformer comes. Then x equal to self dot. So con 2D is already applied in patch embed, right? This patch embed already applies the con 2D operation. So I'm defining patch embed here. Self dot patch embed of x. Then stage 1 blocks and x comma height comma w equal to self dot patch merge. So patch merge we had defined here with the patch merging. So it's the object corresponding to patch merge class x comma h comma w. So h comma w will give us the new resolution after patch merging. Then the new number of tokens is L equal to new h multiplied by new w, whatever we get out of the patch merging. And new number of channels, this is very simple, C times 2. Then x equal to self dot stage 2 blocks of x. Then we do one more layer of normalization, norm of x. So this norm we have defined up here, then fully connected. But before fully connected, we have to do global average pooling. So the last step is x equal to self dot fully connected of x. But before this, we do average pooling. So x equal to x dot mean of dimension equal to 1. So the so that we basically have only batch dimension and just one more dimension for the tokens. Fully connected of x. I think that's it. Then we can just return x. That's a lot of code. I hope everything works at the end of the day. So now we are ready. We are pretty much, now everything is standard. I simply can copy the training part. So we get the training data from data load, this data sets, and then data loader is used for creating batches. These are the only two things which I have not used in the last lecture. These are normalization, standard, mean and standard deviation for MNIST. So these values are famously available on the internet. Then that's pretty much it. And then after this, we can just define the train test loops. So this is the whole code. Now let's keep our fingers crossed and let's see if it works or not. I'm sure there will be a dimensionality error at the part where we, yeah, argument size failed to unpack. I think somewhere we forgot to divide to make it into an integer. Let me ask. These h and w should be integers, but it would not happen if we simply divide by 2. We have to convert it into an integer. So I am sure somewhere I missed dividing. Swin blocks number 2, merge dimension. Yes, that is correct. It should be merge dimension. It should not be the embedding dimension. And because embedding dimension, whatever was there initially would be changed by the time you reach the second stage. Yeah, now this error primarily happens because your number of pixels in your MNIST is so less. So what I am going to do is, this is a little bit of cheating, but that's okay for demonstrative purpose. Here I will not divide the window size, and here I will say the shift is here also. It's window by 2. So I'm going to do that. And then hopefully dimensionality issue should be fixed. Tensor B. And then I will do one more thing. Let's ignore the stage 2. What if I did not have stage 2? So patch merging is not needed because I'm not using stage 2. And then if I run, we should pass embedding dimension to layer normalization. Of course. So that I am passing because here I'm saying merge dimension equal to embedding dimension and I'm passing merge dimension. So I'm just bypassing that. Yeah. So this part is fixed. Where else is the error? Let me do one thing. I have a working code which I just ran just before the lecture. We can compare these two. I'm sure while writing so many lines of code, somewhere some issue will come. So this code is working. It's pretty much almost exactly same as this because I used this code. This code was built with the same purpose, but I just want to know where is the difference. So here I have commented the stage 2 block, but I forgot to comment these 3 lines because if stage 2 is not there, I don't necessarily have to do the patch merging and this resolution adjustment. So these 3 also ideally should be commented. But anyways, let's say I did not do that. And this I kept because although I'm defining the stage 2 resolution inside the class, it's not being used in the forward pass. So there is no harm in just keeping the code there. And here I had done this. See, the shifting was Windows by 2. And the window size, I did not. Okay, here ideally this should be just window. This I forgot to add. So there are a few things. What I will give you as an assignment is instead of doing this for MNIST, because MNIST resolution is so less, there are 2 options. One is you can add a padding to MNIST to make sure that the resolution is slightly high so that by the time you reach second stage or third stage, your resolution is not becoming too small. Because I think somewhere that is causing dimensionality issue. The other thing which I conveniently skipped here is stage 3, stage 4. I completely skipped, of course. I did not try without relative position bias. You could definitely try without relative position bias because in the paper, when they did experiments without any position embedding and with normal absolute position embedding and with relative position bias, they got slightly different results, but not too different. So that is one thing you guys should definitely try as an assignment. So I will give you that along with the code. I'll give you this working code also. Just try running this on your end. I'm not sure if my code is working for any of you because I have made a minor mistake somewhere. I simply cannot figure out right now. So this code, please do try. But see, the accuracy is pretty good. I'm effectively only using one stage, and I mean it's only MNIST, so it should be high. I mean, even any simple classifier can give good accuracy in MNIST. So that is basically it. So I know the parts where I had to go a little bit fast. One part is this squeezing, I mean unsqueeze operation to expand the dimensionality of some variables. So that I have clearly denoted here, like mentioned in the notebook. If I get time, I will record a separate video so that you can go through it on your own time. Anyways, the broad overview, I hope you understand properly, but the main difficulty in the coding part of this is not about the broad overview. It's actually about the getting the code to work by matching all the dimensions. Second thing is, in my opinion, the most difficult part of this is, one of the most difficult parts is definitely the relative position bias. So this will take some time for you to understand. You can, but still here, if you just add a window, sample window dimension, you can just print and see what's happening. That is one part that is difficult. Another part that is difficult is this dimensionality adjustment of relative position bias. Another part that is slightly difficult is adjustment of dimensionality in the masking. Then inside the Swin block, most of the things are fine. Yeah, in the create mask function, there is a little bit of, I would say, finicky things going on in this slicing part. That is another difficult part. I won't call this as difficult. It's just like you will have to pay a little bit of attention to understand this. Another difficult part is window attention and window reverse is kind of easy. If you just write down the dimensions on a paper, you can understand. Patch merging, in patch merging, probably the only part that will be unfamiliar to you from a syntax perspective is only this. Rest of the things are pretty straightforward in patch merging. And in two-stage MNIST also, everything is fine. I don't think if the previous things are clear, I think all the things here are straightforward. Yeah, that's pretty much it. So the most difficult parts where you might want to spend some more time after this lecture is to fully understand the code, is the dimensions, why we are doing this permute operation, which I have explained in fairly good detail, but I'm sure you have forgotten it by the end of coding. So just go through the lecture once more to understand the logic behind this permutation and this view operation. Then go through the relative coordinate, relative bias, position embedding bias construction. Then go through this dimensionality adjustment once. Then go through the mask part also, dimensionality adjustment, and this line of reshaping. Why are we doing this reshaping exactly? Concept, I'm sure you all understand here, but the more important thing is this reshape operation. In Swin block, everything is pretty much fine except the slicing part for mask for window ID. This part, just go through this block, this lines of 4 lines of code a little bit, and I think that's mostly it. Everything else, I don't think you will find any difficult, unless some weird simple syntax issues come. But these are my results. 94% accuracy after 4 epochs, fairly good. I think it's a good point to stop. I wanted to finish by 11 a.m., but took longer than expected. But after today's lecture, I'm pretty sure half of the things you did not understand, mainly because the code is so complex. It's impossible for a human brain to comprehend and think about so many different concepts at the same time. I have gone through this code at least 6 or 7 times now. Even still, some parts still confuse me. I sometimes forget, oh, why did we do this expansion? Why did we do this view operation at this point? So ideally, for me to understand this, I need a piece of paper and write it down. So that's the reason why I put it on Miro. So I also recommend you to just have a piece of paper and write down the dimensions and see what happens when each operation is performed. That's the best way for you to understand dimensions. If your goal is just to have a working code, then I think none of this is needed. You can simply try with Gemini. I'm sure you will get a working code. Second thing is the concept itself, the Swin transformer concept itself, the window shifting part is a bit tricky. If the memory of the last lecture is not very clear in your head today, you might not have understood that. That was a bit tricky part. The third part is the patch merging operation. So there are some finer details in the patch merging operation, which we discussed in the last lecture, which we had to go through a little bit today, but I'm not sure among other details how much you remember, right? So that part you will have to definitely go through once more. But the beauty of learning all these things is that, in my opinion, among all the transformer models we have discussed in this course, Swin transformer is by far the most difficult one so far. In next lecture, so next Saturday, we won't have a lecture. We'll meet next to next Saturday, and we'll be starting fresh because now we are moving to detection. So we'll be discussing about detection transformer next Saturday. Detection transformer implementation will be, I think, in my opinion, will be much easier now that you have gone through Swin transformer. So if you look at 3 models which we discussed. Actually, we have discussed 4 models: Vision Transformer, Nano VLM, Data Efficient Image Transformer, and Swin Transformer. In that, Nano VLM was out of the sequence. I wanted to teach it, although I planned to teach it at the end of the course because it was so related with the transformer ideas we discussed. But Vision Transformer, Data Efficient Image Transformer, and Swin are like one after the other. So Vision Transformer came first, and Data Efficient was a slight extension of Vision Transformer. Swin Transformer was a truly, hardcore extension. So these 3 things, in terms of difficulty, also VIT is easiest, DEIT is the second more difficult, Swin is the most difficult. So if you understand those 3, you will have a fairly good mastery over usage of transformers for image classification tasks. And if you understand even Vision Transformer properly, I think you will have a fairly easy time understanding detection transformer. So detection transformer paper is super famous. I do plan to conduct a little bit of paper dissection sometime soon. But see you all next week. Next Saturday, please note there is no lecture. No, in Swin Transformer, there is no concept of CLS, at least in the main paper. But in the appendix section, they mentioned they have tried with CLS token also, did not make any difference. But there is no concept of CLS token. They directly use the context vector that they get at the end of the 4th stage. Very, very good question, that is. But in Vision Transformer and Data Efficient, there is CLS token. All right, everyone. For those of you who did not get the email, please just put your email in the Discord. I will add you to your... if you just accept the Google Calendar invite, I think you should get an email. But in any case, just put your email on Discord. I'll send you an email. So thank you so much, everyone. Bit of a long lecture, but please go through this once more. I know that this is not the easiest of lectures, not for me to teach, not for you to learn. So I really want you to spend some more time, because the architecture itself is a little bit complex. So we'll meet again after 2 weeks. Take care until then. I'll post a bit difficult 2 assignments in the meanwhile. And if my lecture on detection transformer paper dissection is over before the next lecture, I will share it with you. Otherwise, you can go through it after the lecture. So thank you so much and take care. Bye.